Okay, everyone. Good morning. While we are waiting for others to trickle in, we can kick this off. So welcome to the second workshop for LLVM-AD, so large language and vision models for autonomous driving. My name is Yang Wang. I'm currently assistant professor at Purdue University in the United States. And, we have a very diverse lineup for the speakers today. We have two keynote speakers. Professor Manmohan Chandrakar from UC San Diego, and also he's working at NEC Lab America, and also Dr. Long Chen from Wave in UK. Both of them will deliver a keynote, and Long will deliver that at the beginning of this workshop, and Professor Chandrakar will deliver at the end of the workshop. In between these two keynote, we have I think 8 or 9 talks from speakers in academia. We have people from CMU, UCLA, KAIST in South Korea, University of Washington, myself from Purdue, UC Santa Cruz, University of Tokyo from Japan, University of Gothenburg, and we're gonna wrap up around noon. And I want to, take this opportunity to shout out to the organizers, my students, Yunshen, Ma, and Ken Kui. They are really, leading the effort in putting this together. And also Xu Cao from University of Illinois, Wenchen Ye from University of Virginia, another of my students, Songyang Park from Purdue, Yi Yang from KTH, Amr Abdurraf from Toyota, Junqi Xu from Google, Professor Zhenzhong Tu from Texas A&M, Jiacheng Li, Professor Jiacheng Li from UC Riverside, and myself. We actually, I'm showing this website of our workshop. We actually organized this, the earlier version of this earlier this year in January at WACV. So you can actually click that on our website. It was just January, like 8 months ago, but it felt like a long time has passed because this whole field has been changing so fast, and so many new results has been made by researchers around the world. So you can actually see our first workshop information on the website as well. You can find the recording. We had actually another keynote from Wave earlier this year, who introduced their products at that time, and they have made so many more progress, which Dr. Long Chen will share with us. And yeah, I just wanted to elaborate a little bit on this whole domain before I pass the mic to Long Chen. At the time, back in this June when I visited IV in Jeju Island, I searched around all those papers. I only found 4 regarding this topic, right? Large language models or large vision models, 4 papers during the whole conference. And if you look at this workshop, we have like 10 talks, and you search the program. I think you can easily find like at least 30 papers or related talks in this field. So this is a very fast evolving field. Many researchers have been making progress in this, and we're all really excited about the progress of this field. So with that, I'm gonna pass the mic to Long, who will talk about their work at Wave. Long Chen is a staff scientist at Wave, and who has been doing a lot of work in this domain. And Wave is also one of the leading companies about embodied AI and large language models for autonomous driving. So I'm gonna stop sharing, and Long, you can take away from here.
Okay, great. All right, can you see my screen?
Yes. If you can speak a little bit louder, that would be great, because the audio set up here.
Okay, sure. Is it better?
Yeah, sounds good. Thank you.
Okay, great. All right. Thank you, Zhang, for the very kind introduction. It's my great pleasure to deliver this keynote speech at the second LLVM-AD workshop. And actually, I was able to watch the last recording of some of the previous talks, and I really appreciate the organizers for putting together such a great event and bring together the community who's very interested in the future of self-driving. So today, I would like to share with you some of the interesting challenges and the opportunities in large language and vision models for autonomous driving, and some of the work that I've been working on at Wave. Though I couldn't make it to the ITSC in person due to some traveling difficulties, I promise you that the talk will be equally exciting. So let's get started. So I would like to start the talk by highlighting the importance of self-driving. So why do we need self-driving cars? I believe that everyone here at ITSC shares a common goal to improve the transportation. So transporting people or goods to the destination in an efficient, economic, and safe way is essential to everyone's life. And I personally believe that self-driving cars are not just a possibility, they're kind of inevitable. The reason is very simple, because humans, despite our best efforts, are inherently inefficient, inconsistent, and prone to errors when it comes to driving. So autonomous vehicle has the potential to make our economic better, road safer, and our journey more efficient. So however, self-driving cars are a very hard problem. Despite 20 years and more than $100 billion of investment, there's no company has delivered the safe and scalable self-driving cars. So there might be various of reasons, such as the traditional AV 1.0 usually have very expensive sensors, which is not commercially viable. And also they are usually constrained by the HTTP map and also hand-engineered rules that struggle with edge cases. Also, usually the behavior is very limited to easier driving scenarios, such as highway or very wide roads. So Wave is created to challenge all these points, and we have a different approach. So our mission is to reimagine the self-driving cars with embodied AI, and we call this next generation of self-driving car AV 2.0. And we are building the AI for any vehicle, and we are building for any environment. We are building it to drive in a global scale. So let's have a look at the classic autonomous driving system, which is also called the modular system, or AV 1.0, which usually contains different modules such as perception, prediction, localization, and planning modules. So with such complex systems and so many different modules, the error of individual modules will be compounding and create very big system errors. And also, they kind of usually have many handcrafted rules, which kind of limit the scalability of autonomous driving system into different scenarios or different geolocations. And by using the end-to-end learning, we model the driving problem with a single neural network, which is not constrained by any intermediate representations and allow to optimize the end result directly. So with AV 2.0 system, we show that our car can learn to drive in real world in very complex scenarios, such as like overtaking parked bus or navigating through so many pedestrians working on the road, or different weather, or nudging into the traffic with unprotected right turns. So how is it possible to drive in such complex scenarios without a single line of rules? We found out that with the scaling of the data and the model sizes, the model learns the rule by itself. So here's a very nice visualization of the attention mask on the image patches with our end-to-end transformer-based driving model. So we can clearly see that the model is paying attention to the traffic lights until they turn green, and then shift the attention to the road ahead. So all this just purely learned from data without any rules. And this gives us a lot of confidence that the end-to-end driving is the way to go, rather than handcraft complex rules. You can see here it's a video clip or with our car driving in London, controlled by our self-driving car models. And our model is like so unstructured, our world is like just so unstructured, and it's just like so complex with lots of different cars and with some temporal construction sets, and also with a lot of cars driving in different directions. So it's kind of very hard to write rules for such scenarios. So that's why the end-to-end driving is the way to go. And yeah, there are just like also a lot of like different unusual driving scenarios, such as the car is reversing, and some unusual objects on the road. And we can see our end-to-end solution can safely maneuver to avoid the bins on the road. And also our model can generalize from days to nights in different driving scenarios. So since last year, we have seen that the industrial and the academia shift from the modular approach to end-to-end approach. Especially Tesla claimed that their latest version of their FSD is based on a new end-to-end architecture, which replaced like over 300K lengths of rules in C++. And also in academia, we saw last year's CVPR best paper is Uni-AD, which is end-to-end autonomous driving system framework. Also with different modules, but they are kind of connected together. So however, there are still lots of research challenges of the end-to-end systems. So one of them is explainability. Because the end-to-end approach, it's just like we model the driving with a single neural network. And it's really hard to get any insight from the black box, such as like how do we debug when there are some failure cases, and how do we improve the model, and how do we know what the model is thinking now. And another difficulty is like the end-to-end model usually lacks high-level planning because they usually have fixed context window. So the challenge is how do we add the memory to the end-to-end systems? How do we do common sense reasoning and prediction? And also how do we add the rules if the rule changes? And then how do we add edge cases without retraining the whole model? Apparently, we can solve that with data, but we need a lot of data. And also human supervision are just very expensive. And also edge cases data is particularly rare and precious, such as you can see here a lot of like very uncommon scenarios, such as you can see there's like reflective track in front of you, which I think the model would be very confused. And also the giraffe is working on the road, which is also very uncommon. And also sometimes people are just very creative, trying to fool the self-driving cars. You can see there's a very funny video that a person wearing a stop sign t-shirt was trying to fool a self-driving car. And also it worked. It fooled the self-driving car, and the self-driving car stopped for him. So Wave's solution is to learn the basic principle of the world through vision and language models, which are and vision and language are the most common labels on the internet. So for the large vision model, we basically train the model on the cheap unsupervised video data from the internet or from our data collection. And this helps learning the movement and the physics of the world by predicting the movement of the pixel and predicting the next frame. And for the language set, we use large language model, and we train the model on internet scale text data. And this helps learning human rules and also some of the common sense reasoning ability. And in this talk, I will focus on these two parts of generative world model and or vision language action models. So first, I've talked about our generative world model. So you might think that why do we need a world model? Because like to drive well, you need to able to predict the future, and also different possibilities of the future in order to drive well. And the human is actually very good at this. If you look at this image, you probably think that we're giving way to the white vehicle. But it could be that the white vehicle is waiting us and then merge into the main road later. So we need to really think about like where does human learn this skill from? It's because since very early age of human observations and interact with the environment, we just learn these skills. We learn this skill by observing the cars can drive on the road rather than flying. And we learn that by bumping into other objects, which causes pains, and we can avoid bumping into other objects. And machine learning models should also be able to learn such skills in a similar way by observing videos, by interacting with simulator, and by observing other objects interact with the real environment. And Wave is really investing into the world model from early date. In very early stage of 2018, we published this paper that we can learn to drive from simulation and a world model. And later, we also trained a world model in bird's eye view. And in last year, we have this paper, model-based imitation learning, that we prove that the world model can improve the imitation learning. And last year, we announced our Wave Gaia model. So Gaia is that we formulate the world model as the next token prediction problem using the transformer architecture. And by scaling the data and model size, we are able to generate a plausible video autoregressively conditioned on any given image, any given video, text, or any action. You can see here, we can generate some videos with different possibilities if we sample differently. And more importantly, we call it a world model because we can also interact with the environment. You can see by accelerating or braking the ego vehicle, we can see the other agents is showing different behaviors. On the left side, it's yielding to our ego car, and on the right side, if we brake, the other agent will merge into the road. And here are other examples. You can say Faye driving the opposite lane. The other agent might be just freaking out and trying to avoid us. And we can also control different weathers from the text and also control the time of the day by just inputting the text of like what weather and what time do you want to generate. We are also able to generate very long videos by just autoregressively generate videos. You can see even with minutes long of video, we are still to generate very in distribution data. And here's also some examples that we can control the action of the ego car. And here are more cases that we can also control the agents, the other agents. So for the world model, there are lots of opportunities ahead. We can integrate the Gaia into Wave's on-road driving AI, which our driving model might be able to think about different possibilities and make a safe decision. And we can also further scale up our world model and make the generated images looks better, also integrate with multi-view generation and multi-sensor generation. And also Gaia as a world model It's also a learned simulator that we can use to train and evaluate our driving model. All right, coming to the second part, the vision language action models. So again, why do we even need language in driving? It's because that the traditional rule-based driving model usually struggled with debugging the models. You need to look at the bounding boxes and all the if-else rules. And also, it's not robust to auto-distribution scenarios. And it's also non-scalable. If we use language for driving, for interpretability, we can just like ask the model, what are you doing? And the model can also comment out their behavior. And also for long tail scenarios, it has very nice zero-shot reasoning ability. And for scalability, the language model has the knowledge from the whole internet that we might be able to leverage in the edge cases. So last year, we proposed a novel proof of concept work that we can interact with a simulated environment where we have access to state vectors such as the route, vehicle, pedestrian, and vehicle states. And we use a combination of the vector encoder, transformer layers, and a large language model with long-run module to make the driving decision and explain the reason behind that. Then we can use this action to control the car in the simulated environment. And here's a short video demonstrating the model doing this different task, including the action prediction, action explanation, and also the driving question answering in an open loop setup. Here are some like qualitative examples showcase that the model can do different tasks, such as reasoning about the actions, predicting the future, and also can answer questions about the perception, also some general tasks, such as like how do you change the tires? And also it has some ability to prevent hallucination by rejecting the question. So that was our first proof of concept in early last year, when the large language model just become a hot topic. And I think this year we saw a lot of open source the vision language model. And in another work in this year, we proposed a new vision language action model that we can directly input the vision input and making the driving decision on it. So we call this architecture Lava because we use a Lava vision encoder. And we can see that the model can comment about the reason that it is driving, such as waiting for a gap in the traffic. And then you can see the model also drives very well in a closed loop setting in Kala. And this work won the best solution in the Kala Challenge 2024. So this work are all just proof of some concept in simulation. The problem is like, how do we incorporate a large language model into the real world driving? And how do we extend the vision language action model into video language action model? And most importantly, how do we align the vision language model with human intentions? And we propose this Lingo model. So Lingo model is a real-world grounded video question answering model. We use a BLEEP2 inspired architecture because it has less number of tokens. And we also use a video late fusion strategy to fine-tune the model. And in the Lingo QA paper, we also propose 3 data sets. The action data sets contains lots of the real-world driving scenarios that contains reasoning and the intention from the driver directly. And that's a very good source of to align the driving model with human intentions. Evaluating large language model is also a hard problem, and we also propose to use learned a large language model to evaluate another large language model. And we show that with this learned metric, we achieve much better correlation with human evaluations. Here are some example of the LingoVan model. Again, LingoVan model is just a commenting model. It cannot drive yet, but it can do commenting based on your driving decision. And it can also do vision question answering, such as you can ask like, what's the weather, it's raining, and do you drive differently? I need to be more cautious. And the LingoVan can also do referral segmentation, such as if you ask what are you paying attention to, it can output the answer and also referring to the segmentation of the image. So this is kind of like a better grounding of the language and also segmentation modality. We further extend this work into Lingo2. So Lingo2 is a real-world grounded vision language action model. It's because we added these learned queries that we can output the driving action based on all this vision input and also the text modality. Here's a short video of the Lingo2. You can see that this video is a recording of the Lingo2 model controlling the vehicle. And also you can see the Lingo2 model can comment about its current action. So here are also some challenge scenarios, such as reducing the speed and change lane. And stopping for the right light. And it's also very important to evaluate how your language and action are aligned. So we have a simulated environment. You can see on the left side, we have this dynamic agents. On the right side, we have an empty road. And the Lingo just output different commentary about what it will do in the future. The left side will be stopping for pedestrian on the zebra crossing. And the right side will be accelerating from stop because the road ahead is clear. And you can see from the speed that the action is aligned with the language. So the next property of the vision language action model is that you can control the action with your language prompt, such as if you prompt the model with different instructions, such as turn left, turn right, stop behind the bus, or overtake the bus. The model will actually generate different actions. So this will also unlock a lot of possibilities of controlling the vehicle with natural language. So our future would be unlocking the embodied AI with a foundation model that combines all this vision language model together into a single foundation model. So we can just, if we have all these different input modalities and the output modalities, we can just join train a foundation model that learns everything. And this will enable truly embodied intelligence. So to summarize this work, to summarize this talk today, so we talk about the AV 1.0, which is usually the rule-based approach, contains the perception, planning, and prediction module. they're really not robust to auto distribution, and also it's really non-scalable. And for AV 2.0, so if we just use the data-driven approach, that would require a lot of data. But if we learn the world with a principle-based approach, such as we have a word model to predict the future, we have the vision language action model that has the knowledge from the internet and also some common sense reasoning ability. So we have the benefit of the knowledge from the whole internet. And then the model can do zero-shot generalization, and it can reason with a chain of thought or other techniques in the large language model space. And that will be the future of autonomous driving. And Wave is pioneering this principle-based autonomous driving, combining with large vision and large language model. So that would lead to the end of this talk. And we're hiring in London, Silicon Valley, and also Vancouver. And we're looking forward to you to join the journey of building the next generation of embodied AI. Thank you so much. I'm happy to take any question.
Thank you, Dr. Chen, for a very good talk. So we have time to take a few questions if our audience have any. Yes.
How do you define the end-to-end model? So does it mean just we don't have separate modules for perception, planning, and control, or it's more than that?
Yeah, our audience has a question alone regarding the definition of end-to-end autonomous driving. How to define it? Is it just separate, compared to the previous one that has separate module? For end-to-end, just one single module, or do you have more concrete definition for end-to-end autonomous driving?
Yeah, it's a great question. I think the end-to-end, so our definition is that we use a single neural network to model the driving problem without any of this perception, prediction, or planning module. They're kind of combining together into a single neural network. But more broadly speaking, there are also other variations of the end-to-end approach, such as the Uni-AD, which is kind of like a modular end-to-end approach, although they have different modules still, but they're connected together, and during training, the laws can backprop to different modules and optimize each modules. So there are like different trade-offs between different approach. But I guess the most important part of the end-to-end network is that you can join to optimize all these different modules whenever they're different module or a single neural network. They're all considered as like end-to-end neural network.
Yeah, thank you. Any more questions?
So you showed you can command textual or give textual commands to the vehicle, but it was rather one activity. But people who really understands an environment can get something like, go down the avenue, after 3 intersections, go right, and then follow the path until the red office building. Is this possible with this model? Because it would show that car really understands the environment.
Yeah, so our audience has another question regarding your large vision model, where you show that your model can understand like one step further for the action that the vehicle needs to make. But our audience had a concern or is curious about whether you can reason multiple steps ahead. Like you go ahead and then you turn right and you park at a parking slot or something like that. So he was wondering whether your model can make multiple actions or predictions in the future like humans does.
Yeah. So to answer this question, I guess a nice property of our generative world model is we're doing this autoregressive generation. That means we're generating conditioned on anything, such as if you give it a single image like this, it can generate action by itself and also generate the image, and then autoregressively, I mean, like it will also condition on your past generation and generate continually, just like you can generate like minutes long of video. But this is just for video generation. So I guess what the question was like, if you can make your driving model really planning for a long sequence. I guess it's still a kind of ongoing research, because the currently world model is very slow to generate, because it's generating these pixels, which contains a lot of like high frequency details. I guess like in futures, maybe we can generate states or embedding without decoding into the radio, so that you during driving you might be able to do this kind of like Monte Carlo tree search by just iterating all the possibilities, and then you choose an optimized solution to drive. But this is still like ongoing research direction. Yeah, I hope that answers question.
Okay, thank you. Any more questions? Yes. Yeah, go ahead.
So vision large language models did hallucinate. If yes, what are the techniques that they follow to mitigate them?
Our audience had a question regarding hallucination, whether there was any instance of your LLVMs that has hallucination, and what are the potential solutions regarding that?
Yeah, I guess hallucination is kind of very common in large language model. And it's also a very hard problem, not in driving scenarios, but also in other large language model, such as like ChatGPT sometimes also hallucinate. But in terms of driving, I guess it's more critical, because if you hallucinate something, you might lead to an accident or something. So in our previous work, we kind of prevent the hallucination by doing some, including some of the like unrelated questions, and we supervise this by just not answering this like unrelated questions. But this usually requires a lot of data to do supervised fine tuning. But I guess to further align this vision language model with human preference, we can also try to leverage some of the techniques such as RLHF or DPO to reduce the possibility of some negative examples such as hallucination. But generally speaking, I guess this is definitely some problems of constraining from using large language model in driving. And we definitely need to put more resources into researching this problem.
Thank you. Any more questions from the audience? Yes.
What's the typical runtime of a model like this for real-world inference?
So the audience was asking what's the typical runtime for this kind of models I just show for real-world inference and real-time inference.
For the one model, it's just generating videos, so we haven't used it on road. But for this Lingo 2 model, so the video showing here kind of all the recording of the model controlling the vehicle. So that means that our model must be running at a like relatively fast speed. So currently our model runs at like 10 Hertz, because we're kind of limiting the number of tokens we sample of the language. So if we even don't sample language, the model might be running even faster. Also, we are using a relatively small language model, such as like we use 2 billion size. that can also run faster in our car. But our car has like very powerful GPUs. But there are some like other ways you can make the large language model makes running faster and also the size smaller, such as like quantization or other techniques.
Yeah, thank you. I might take the liberty to ask the last question, Long. So regarding our end-to-end autonomous driving models, I'm just curious, when you have by-wire control at your last step, right? You directly output your command to the vehicle based on our end-to-end model. Do you have any safety filter that can guarantee the outcome of your end-to-end model is reliable, can guarantee like all the safety constraints? Or you just directly input your end-to-end model output directly to the vehicle control?
Yeah, that's a great question, and I guess that's kind of like an active working direction we're currently working on. And currently, you can see the output, just the waypoints. You can see the trajectory is the green curve is the output of our end-to-end model. And we do have a controller that converts this trajectory into feasible actions like steering and acceleration brake. And we do have some like a smoothing process to make it smoother. And we are also working on adding some safety constraints to such as you can limit the steer ratio or accelerate the brake ratio to make it drive more smoother and cautiously. We are also considering adding different sensors such as radar that can detect the obstacles and avoid the obstacles. But in general, we're kind of safety is our top priority, and we're definitely working towards to make the end-to-end model drive safer in the road.
Sounds good. Let's give another round of applause to the speaker.
Thank you so much.
Yeah, thank you, Long. So our next speaker is going to be Sean Naksuro from CMU, Carnegie Mellon, where he's going to talk about context VLM, zero-shot and few-shot context understanding for autonomous driving using vision language models. Yeah. Can you log into Zoom so we can share the screen? Do you have that? You have the link, right? Yeah. While our next speaker is setting up, so for the next 2 hours or so, we're gonna have 1, 2, 3, 4, 5, 6, 7. We're gonna have 7 more brief talks. Each talk will be around 15 minutes. And actually, each of those talk, you're gonna have a chance to visit their presentation during ITSC for a longer version, where they will present the papers either in invited session or special sessions or regular sessions during the future days. But we invited them to give a summary talk kind of thing on this workshop to brief everyone about the progress made in this domain. And
Oh, hi. It looks like I cannot. You mute your mic in Zoom.
Share screen. And just mirror screen.
Yeah, I have heard it, I think.
Okay.
Let's see now. I think it takes some time to come.
Okay.
It usually takes time.
What's that?
It usually takes time.
Okay.
Yeah.
Okay. Yeah. So as I was saying, I'm Shaunak, and today I'm going to talk about context VLM, which is our work on zero and few shot context understanding for autonomous driving using vision language models. So we start with the following motivation, which is that for autonomous vehicles to be able to drive everywhere, it has to also drive in very specific scenarios that are difficult for AVs to handle. So that can be things like parking lots, tunnels where you see loss in GNSS signals. It can be dense urban environments. It can be conditions such as snow, rain, etc., where some of the sensors can get impaired. And these are various challenging but also safety critical scenarios. Now, there are two main types of AV architectures as of now. One of them starts with sensor data, and then it has an end-to-end AI stack, which results in some action plans or control signals. But there's also the modular AV architecture type, which we have at CMU, which is composed of perception, localization, behavior planning, and so on. Now, the end-to-end AI architectures can be prone to out-of-distribution generalization issues and also to lack of explainability in case of failures, whereas modular AV architectures have various specific components that function together, and it is easier to debug in such cases. But also, this comes with the drawback that sometimes modular AV architectures require specialized modules for handling operation across various driving contexts, which are effectively things like the parking lots, tunnels, etc., that I showed you in the last slide. So this work focuses more on handling those special cases in modular AV architectures. So by driving context, we refer to various situations like lighting conditions, weather conditions, whether the car is driving in an urban canyon, in a city where you often see loss in GNSS signals. It can also be driving in a parking lot, as I said, and also in tunnels. So these are quite a few driving contexts that have to be handled by autonomous vehicles for their large-scale deployment. Now we'll talk a little bit about context understanding, which is something that we describe in this paper. So we curated a list of about 24 contexts which are relevant to AVs, and this list can be extended based on applications, but there are various contexts that affect various parts of the AV subsystem. So the lighting and weather condition can affect the perception stack. Um, the location of the operation of the vehicle can affect planning, behavior, and even localization. And we have seen in our prior works in this domain and also works by other authors that, for example, in perception, sensor domain knowledge based on the operating conditions, such as whether the autonomous vehicle is operating in rain, night, or snow, or an urban or rural environment, can uh, improve a lot with performance, can improve performance by a lot. So this additional information is often helpful. Even for localization, there are methods that rely on vision-based localization when, again, GNSS doesn't work as well. And these things can also benefit from the knowledge of the fact that the vehicle is operating in a specific environment. We have also worked a lot with work zones or construction zones, which often you see a lot on the roads, and there have to be specific AV modules to deal with this because this doesn't expect standard behavior. So the knowledge of these specific contexts can help a lot with the next steps. So towards this, we propose a driving context dataset that we create. This has about 66,000 images with 1.6 million image and question answer pair annotations. In this case, question answer refers to a question about what the driving context is like, and then the answer would be a binary answer saying whether the driving context matches a specific one out of the ones that we define. And as we can see here, these are a couple of images that are recorded by our CMU AV, and we annotate these with various driving contexts of interest in terms of these image and question answer pairs. And we also see that in our data set, the distribution of context has a long tail distribution, which is quite common in autonomous driving applications. But given a long tail distribution like this, it is typically difficult for supervised learning methods or computer vision methods to predict in the case of rarer contexts. So to solve this, we present a simple but effective method using vision language models. And our dataset has two subsets. One is a hand annotated subset and a larger machine annotated subset, which has been annotated with multiple VLMs, each with a high confidence threshold and agreement among those. And the dataset is composed of images from kitty new scenes, ones that are recorded by our CME autonomous vehicle, which is in majority, and some royalty-free web images. We make this dataset public as well. Now we move on to the approach. So the idea is pretty simple. What we want to do is take the autonomous vehicle images that are captured and then ask questions such as, is this during nighttime? Is this in a construction zones? Are the lane markers clearly visible, and so on? And this is fed into a vision language model along with the images recorded from the AV camera. And finally, we have binary answers of each of these contexts per image. Now we experiment with two main models in our work. One is WILT, which is the Vision and Language Transformer, and LAVA, which is a more recent visual instruction tuning model. And we use these models because these are on sort of two ends of the spectrum, because LAVA is much heavier with 13 billion parameters and WILT has about 87 million. And also WILT is meant more for simpler VQA tasks, while Lava typically works with more specialized prompts similar to how ChatGPT would work. And now, finally, we evaluate the zero shot and few shot capability of these models for the tasks that we have designed. So now we move on to evaluation. So one thing that we find is that in general, WILT tends to perform better than Lava on our dataset, although WILT has much fewer parameters and is a simpler model. And by this, we show that even if the model is larger and it takes a lot of time to run, there can be simpler models in the vision language domain which can do the job at hand. And with this, we get about 93% accuracy on the whole data set, with slightly higher on some subsets. And we also see that it will, of course, performs better than Lava, although it's only by a little. And in future, we are also planning to explore other strategies from the era of natural language processing, such as chain of thought prompting and auto prompting, which can potentially lead to improvements with methods like Lava. And across the 24 contexts that we have selected in our driving context dataset, most of them end up having over 90% accuracy, while some classes like tunnel and bridge, which only are very few in our dataset, end up having pretty good accuracy because of the zero shot capability of VLMs. But some instances, such as lane markers, are more difficult as of now, mainly because of the presence of other road markers such as crosswalks and so on. And all of this slide is with the WILT model, because this was the better performing model among the two, and we conducted further experiments with this one. Although for things like lane markers, it might be possible to use more better reasoning strategies with a larger model to potentially improve performance. Now we move on to an ablation study on our dataset. Our dataset has two components. One is the hand annotated component, and the other one is machine annotated. And in this, we start with WILT, which is the vision language transformer trained on about 4 million images from the web. And then we use some labeled samples from our driving context dataset. And we see that the few shot capability of this model for this task is quite good. And with about 64 shots or so, the accuracy can improve by about 5%, and F1 score improves by 10%. And it is able to detect the driving context much better. So what this means is that if you have a task where you need to detect such driving context, you can just take a few images, maybe of the order of 64, hand annotate them, and then just fine tune with a strategy like this to get pretty good performance. And this is in contrast to existing literature, where often recognition of driving context involved a few specific contexts and more supervised learning methods. And here we are dealing with about 24 contexts, but it can be extended for various other contexts that you might come up with and are necessary for your modular AV to work. Finally, we also evaluate the capability of real-time inference with our model, where we first compare lava and wilt, and we see that, and we do this on a pretty lightweight A4000 laptop GPU, and we see that wilt is much faster and also performs slightly better. So we actually deploy the wilt model on our semi-autonomous vehicle, which I'll talk about in the next slide. But we do try to reduce the runtime of Lava a little by creating a joint query of all of the driving context together compared to individual questions. That does reduce the runtime by a little, but still a much lighter model works better and can run relatively fast. Although Wilt is relying on more simple VQA type questions compared to Lava, which can use prompting and better reasoning. So this is the CMU autonomous vehicle that we have in our lab, and we have fine-tuned the Wilt model, which ran faster on our dataset, and then finally deployed it on the CMU autonomous vehicle. And then we drove around Pittsburgh, Pennsylvania in the US to see that things like urban canyons are detected pretty accurately and doesn't require many hand annotated samples for this to happen. The reason this is useful is because many localization algorithms, for example, rely on GNSS as one of its sources. And in urban canyons, we see regularly observed loss in GNSS accuracy. And with our model, we can detect this beforehand and then kick in specialized modules which can deal with those things. And the latency on our autonomous vehicle with pretty lightweight 4 GB GPU is about 10 milliseconds per query. So in summary, we have developed a method called context VLM, which is used to deal with the task of context understanding, which is quite relevant for many modular AV architectures. We have designed a dataset called the driving context dataset that has about 1.6 million image context pairs. And our method is easily extendable to new contexts that might be relevant to an AV because of the few short nature of the problems being solved. And in future, we can use more reasoning-based methods to improve the understanding of such contexts. And the detected context from our VLM can also be integrated with larger VLM-based planning methods to potentially improve driving context with additional domain knowledge of these known real-world driving contexts. This work was funded by the US Department of Transportation, and thank you very much.
One question on the audience? Probably. I'll take one. So you talk about the average latency, which is 10 milliseconds, which is impressive. I'm wondering for the usage of such scene understanding message, because from my understanding, if you just want to do some image classification, you have tons of existing traditional computer vision algorithms that can do the things for you, right? Whether it's a tunnel, whether it's foggy or things like that. So I'm curious, how do you use this inference outcome to your subsequent planning or control? Do you have any plan for that?
Right. So effectively, this is so we have already used this a lot in perception. So for example, we saw that perception performance with LiDAR and camera-based fusion methods can improve a lot if we have the knowledge of nighttime or rain. And this is something that we have tested and basically deployed. For planning, for example, there is one specific use case that we deal with a lot, which is work zones, where if we detect something like that with the method, with our method, and it's detected in something like 10 milliseconds, then the output of it can be fed into regular planning stack where this is sort of an additional flag which can be used to kick in more works on specific applications.
All right, let's thank, oh, you have a question, that's right.
Yeah, so you fine tune both models?
Yes.
How much data did you use?
Yeah, so we mostly work with the fine tuning of the built model because it was more lightweight and practical. And about data, we do have a data set of which has 66,000 images and about 1.6 million text and image pairs. But finally, for fine tuning, we show that we can get pretty good performance with only about 64 or 256 data points. Yeah.
Yeah, let's thank the speakers. Our next talk is from UCLA. Speaker is Ethan Liu, who will talk about semantic trajectory data mining with LM-informed EOI classification. Yeah. Your audio. Okay, great.
Hello guys, my name is Ethan Liu. I'm from the mobility lab from UCLA. Here we are working, our lab is focused on to provide innovation solutions to new mobility questions. So today I'm here to bring my work with my colleague Haoxuan Ma, the named semantic trajectory data mining with LM-informed POI classification. Our presentation will go following the 4 different parts. I will do the introduction and methodology, and my colleague Haoxuan Ma will go over the experiment and the conclusion and fieldwork part. So in those years, as the development of IoT devices and also personal devices which have the GPS function, like laptop or mobile phones, the trajectory data with GPS info get flourished and bring us a new way to new era of data collection. And however, like in those trajectory data set, there are only things like state points and also the time steps, which is only the spatial and temporal information, but it's lack of semantic informations. The semantic informations are extremely important in understanding people's traveling intentions because like most of the travel demands is contributed by the function of the locations. And those semantic informations could help us better understanding the mobility patterns. For example, people will go restaurant for the dining, and people will go to theater for entertainment, and people usually go to the gym will usually contains activity like exercise, and schools will always will usually contain exercise activities like classes. And we would like to review these like hiding semantic infos behind the spatial temporal trajectory dataset. And here is our objectives. We want to combine the spatial and temporal trajectories with relevant semantic informations to create a more generic and effective tools for automatically annotating large-scale dataset. And we wish our work could bridge the spatial temporal information and natural language analyzing trajectory mining and open a new avenue for the mobility research. And I will first give an overview of the point of interest, which we have value used in our experiment. So POI data set stands for point of interest. Are those like geolocations, geolocation we are interested in, and those points are usually the name of usually the location of some either the restaurant or the like work location or a school location or either the individual home location. So based on the concept that the people usually travels, the human travel pattern are revealed by the function of the location. So combining the trajectory with semantic information behind those POI data, we wish to reveal the intentional activity for people traveling purpose. At the right-hand side of the slides, we can see a POI example. It's like ABC gas, and the amenity type is retail, and the POI data set will also include the latitude and longitude information. And in our study, we are focusing on the following like 15 activity types that we review from the National Household Travel Survey dataset. So our task breakdown will be the first. We will integrate the activity information with locations on the map based on the POI dataset, such as in the previous example, we wish to labeling this POI example like ABC gas into a category of buying goods, like buying gases or buying other services. And after labeling, after we get the activity information hiding behind the point of interest, we will infer the purpose of each trajectory data points based on the geographic location information and also the nearby point of interest of that trajectory C point. And that is to infer the type of activities. So about the current research gap. So first is about the POI dataset. The POI dataset is inconsistent due to its nature of collection. Because the POI dataset is a really large dataset, it involves a lot of like human labeling variants. For example, in the OpenStreetMap dataset, it will involve volunteers to do the labeling, and the volunteers without like a really specific training will have like different like labeling styles that will make the dataset inconsistent. And also currently for the POI classification task, which classify point of interest into different activity classes, well, like mostly based on the learning-based method. The learning-based method like relying on the neural networks which require like high level of data integrity because they need to like use all the available variables. However, those learning-based methods, like when facing into the real-world data set, I just mentioned, which involve a lot of like data inconsistency, have a like not good performance. And besides the POI classification about the activity inference for trajectory. So for the like mandatory trajectories, which is highly have a like strong periodically, like home activities, work activities, or school activities, the rule-based method do a good job. However, when going into some like non-mandatory activities, for example, like social activities, like go to exercise or go to entertainment, which is like not that strong periodically, and the traditional like rule-based method feeling struggles, and because they are lacking of because those activities are like strongly linking with the social behavior, which need like more semantic information for understanding that. So here is our workflow. So it will be divided into the two parts. The first part will be the POI classification, and the second part will be the activity inference. So in the first part, the input will be the POI, the point of interest classification, into a large language model. We will input the POI observation as well as the task description and the category description to form our prompt. And then the LLM will give us the top 3 most likely activity type with their probabilities. In the second step, we will use those classified POI informations as well as the trajectory data into our activity inference algorithm to predict the activity types for each state points in the trajectory. So here's our structure here's our like prompt structure for the POI classification part. It will include like basically 3 parts. It will include a brief test description to describe what our work is, and also activity type dictionary, as well as available information from the POI dataset. Note that the available information from the POI dataset will not always complete. So it will leak some. So in the real world case, it will leak some information like amenities or other stuff. And for example, in this example, the outcome of the classification will be, it will successfully include predicts the Papa John as a as a category 7 by Muse, and also 20% of probability of activity type 5 by Goods. And about our activity inference, because for the manager activity, the rule-based method have given like really good performance, so we will use our rule-based for the manager activities. However, for the non-manager activities, we will use the probability approach to do this. And we will like calculate all the probability pairs for each POS and the candidate activity types, and based on the Bayes algorithm, and we will choose the highest most likely to happen activities as a classification result for the activity type for the state point. So about the experiment, I will introduce Haoshuan to go over this.
Okay, so after we talk about methodology, let's take a look on the experiment. So the first is that we utilize 2 types of data set. The first is the POI data sets that we collected the real world data set from Los Angeles County and also from Egypt, both using the open source map called OpenStreetMap data. And OpenStreetMap is a public source data, so it has a lot of inconsistency across different contributors in the society. So basically, without excluding mandatory features like name and latitude, longitude, all the other features are optional. And so we have encountered problems like 89% of feature are missing in Egypt POI, and similar for the LA POI. But and then it's a trajectory data set. So for trajectory data set, we mainly used it for our LA County's experiment. We have a daily trajectory activity trajectory generated from the NHTS, which is National Household Travel Survey, and also because the accuracy diminished in urban environments near structures like buildings, bridge, and dense foliage. So in order to evaluate our performance and robustness against the real world condition, we introduced noise at 3 levels. Basically, it's 5, 10, 20 meters. And so those noise are assigned based on a Gaussian kernel, and it's added to the latitude and longitude of the POIs. And the next is the result analysis. The first is, let's take a look on the POI assignment result. So as we can see from the 2 graphs, on the left-hand side is the LA County result, and the right-hand side is the Egypt result, which features in different cities. And then for LA County, as we can see, like LLM is able to support semantic inference. Like its large-scale pre-trained semantic knowledge is able to make inference on commercial names like KFC. So the LLM instantly know that KFC is a place of getting food. So it gives a 70% of probability of buy food for a POI name called KFC solely. And then also it gives a good semantic reasoning power, like by giving 2 standard contexts like diving and near the beach. It would just give activity classification like exercise. And similarly for worship place, it would just give a give activity type of religious for the most probable activity. And Then it will for like for place of like multifunction like a cafe. Mainly like it can be used for buying food, like dining, or used for recreational social gathering activities. So like for the POI3, basically it can give a quite similar activity for both like buying food and recreational with a 50 versus 40 probability. And then it's for robustness, as we can see on the right for the Egypt OSM, we have a lot of Arabic names of POIs, but without pre-training with any other language, the LLM automatically know like different activity types and the performance we can see on the next slide. So for the POI accuracy in either Egypt and LA, it gives a pretty good accuracy. And how we get the evaluation is we manually label 500 observation from each POI dataset from Egypt and LA. And of course, we translated the POI in Egypt for the human labeling. And we can see the accuracy are pretty good, around 90% for both GPT 3.5 and GPT 4. And and for the hit rate is what we define, like when GPT assigned 3 most probable activity types, and for what is the range for the GPT hit the human label activity type. So and then there's the spatial temporal analysis. In this case, we can see for two trajectory we extract for the activity inference. It gives a pretty good reward. It makes pretty good reward sense, and also make traffic theory sense, like a activity pattern of like homework, home, and along with short periods of like visiting activities or like exercise activities. And all the start and time makes pretty well sense for the POI assignment. And then it's the result for the activity inference algorithm. So we can see for mandatory activity assignment, which we incorporate with the rule-based code, like we can see the accuracy at the top one hit rate is around 90%, and as well as the F1 score is very high. And for non-mandatory activities, we're generally doing a not bad job, but for some like activity types like visiting friends or drop off pickup or like exercise, it typically incorporate with the it's not like very dependent on a POI type. So any place can happen for visiting or like for drop off and pickup. So for those accuracies, it is not that significant, but mostly for very POI related activities, we have a good performance. And then we also test on the level of noise based on the POI arrow that we intentionally assign. As we can see, for a smaller noise, the better the performance could be. And for the top view activity at the 5 meter, we can reach around 90%. And so for the conclusion is we provide a novel framework that connects the traditional spatial temporal analysis that giving by coordinates and timestamps, that we can give them semantic meaning based on like this the current power of LLM. So it can provide new research opportunities for mobility studies, like and then the robustness of the LLM can be well evaluated, since we can now without extra training, we can still achieve a very good performance and based on a very incomplete open source data sets like OSM. And the accuracy, as we can see in summarize, is pretty good. It's all around 90%. And in the future, we can improve this whole pipeline by incorporate more large language model fine-tune techniques like prompt engineering, or we can do like supervised fine-tune, or even like reinforcement learning on this specialized tasks. And then we can also, based on our trajectory inference assignments, we can innovate more downstream tasks like multi-day trajectory analysis, or like generation works in the downstream. Yeah, and that's basically wrap up our presentation today, and we can take any questions.
Let's take one question. So probably I'll take the liberty again. I can see clearly, how this thing can be used for navigation purpose for autonomous driving, right? But I'm just curious about the results that you show for the accuracy and F1 score. Is there any discrepancy between the data set of LA and Egypt when you have shown all this accuracy? I'm not sure whether there's any difference in between the results from both data sets.
So you're referring for the POI inference of the LLM result?
Yeah.
Yeah, so there's no significant difference, even they have a different language. So that's we will try to prove like the robustness of our method.
So pretty much it's agnostic to any kind of language as long as it's the data has certain format and then you can use your LM to process.
Yeah, as long as I have a name and like necessity features.
Okay.
Yeah.
But what about the quality of data? I know those two data set have similar quality, but if you have a much higher quality of data set or a much lower data set, does it matter? Do you think will?
Yeah, so we're basically in our prompt query, maybe you can take this question.
Yeah, like in our prompt query, like most, I believe like most of the classification are based on their names because the names will reveal like a lot of information of the POI. So I think as long as we have like a representative name, we'll have a like good result.
That's good. Yeah. And thank you. Our next talk is gonna be from Kais. Dr. Rigas.
And we will talk about the multimodal warning system for drivers.
Yeah, so just share. Okay.
HDMI.
Okay.
Yeah, right.
Share screen. Good morning, everyone. I'm Zixuan Xu from Human Factor-Centered Transport Safety Lab in KAST. It's my honor to be here to present our work on a LLM-based multimodal warning system for driver assistance. Today's presentation will be structured into 5 parts. First, drivers interact with the warning system through human-machine interfaces. The effectiveness of warning system heavily relies on the design of the interface. Poorly designed warnings may distract drivers and cause discomfort, while user-centric approach enhance information comprehension and acceptability. Then how to design a good human-machine interface? We may get some inspiration from real-world experience, which is typically multimodal. Such visual, auditory, and tactile senses helps our brain to interpret the world around us. Also, research indicates that in high cognitive load condition, multisensory clues significantly improve the performance compared to unimodal alone. And driving itself is also a cognitive task. Inspired by this, many researchers have applied multimodal warnings to different types of driver assistance functions, such as fatigue warning and collision warnings, and they prove that multimodal warnings result in faster reaction times and enhance the situation awareness. However, human drivers, they have different hazard perception skills and interaction preference due to their unique characteristics. And despite the advancement, it remains unclear which multimodal configuration is most effective for different driver groups across different warning contents. And therefore, there is a need for an adaptive and personalized warning system that can intelligently decide on what to warn about and how to communicate with driver. On the other hand, large language models and multimodal language models pave the way for knowledge-driven assistive system as due to they exhibit emergent abilities in accepting multimodal input, perform explainable reasoning and decision-making, generate human-like content for human-machine interactions, and they can also learn from the new knowledge and the environment. Therefore, our research aims to develop a LLM-based multimodal warning system that could work as an expert, identifying the driver's special needs for human-machine interaction and their safety concerns while driving, and a detector recognizing potential hazards in the traffic environment, and also an assistant that provides warnings to drivers through suitable interaction modalities. Here we define 3 types of modality: visual, auditory, and haptic. This is the framework of our system. It's agent framework that contains 4 different modules: memory, perception, control, and action module. To ensure efficient response, a personalization profile will be initialized first when the driver first time operates on the system. The personalization profile will work as an instructor for the system to work as a personalized driver assistant. Then I will introduce the different modules separately. The first method we use is retrieval augmented generation. It's a method for large language model to learn external information from the database and have been applied for content generation for specific domain. This is how the basic RAG works. When the user input queries, the retrieval model will retrieve the relevant data from the knowledge base, and the relevant data together with the query will be put together into the pre-trained large language model. The large language model will learn from the relevant data and generate a more reasonable response. Because the basic RAG have some limitations, here we propose a types of advanced RAG for personalization profile generation. The input is the driver profile, include personal information, driving experience, and their driving habits. After input the driver profile, the multi-query generator will analyze driver features that influence their driving and the interaction with the system and generate questions related to the features and the interaction. Then the retrieve agent will retrieve the relevant data from academic materials. Then the driver profile and related knowledge will be put together into the large language model. Large language model will conduct reasoning and generate the personalization profile. The personalization profile contains driver feature analysis and related knowledge, and also interaction for the multimodal warnings, including their description and the application scenario. And finally is the safety concerns about the driving. The personalization profile will be stored in the memory module. Here is an illustration of the control module. It contains 2 parts. The first vision language model will conduct scenario reasoning to list all the traffic elements in the environment, and another light large language model will work as a driver assistant. To invoke its capability, work as a driver assistant will apply chain of thought prompt engineering. First, let the large language model rank the hazards, choose the hazard to 1 and then based on the driver profile, choose the interaction methods for each hazard, and finally utilize the tools to perform the multimodal warnings to the driver. For the action module, currently action module contains a set of predefined tools for multimodal warnings. Currently, we have basically defined 3 types of multimodal warnings, including visual, auditory, and haptic warnings. The tools in the action model can be flexibly updated and expanded. And also here for illustration, we use 3 types of driver to demonstrate the result of our system. Non-voice driver, old driver, and foreign driver, each of them have different driving experience, physical conditions, and the accident history. And it's a result of the generated personalization profiles. In fact, due to page limit, we only show the simplified versions. In fact, it's a more comprehensive one. From the results, we can see that the system identifies the driver features that influence the driving and the interaction, and based on the features and knowledge, they give the interaction strategies for different mobility of warning, and also offer unique safety concerns for different drivers. We also evaluate the agent's performance using 53 diverse traffic scenarios. This is a record of how the system performance in an interaction scenario. From the results, we can see that the system offers different types of warning contents through different mobilities for individual driver, and also offer reason. The second scenario, the second example demonstrates that even for the same warning contents, the system can choose different interaction methods to warn the driver, and also give the reason. Here is a result of the system's performance across the 53 scenarios. The percentage of different mobilities. From the result, we can see that the percentage of different mobilities align with the personalization profile that's generated by the system. For example, for the old drivers who have glaucoma symptoms, their primary interaction methods is the auditory tools. The systems increase the auditory warnings, uses over visual warnings, and the haptic feedback in this case provide attention situation awareness in complex driving situations. This indicates that the system's performance aligns with the personalization profile, and it reach a level of personalization to generate warning contents for driver with different characteristics. In conclusion, in this work, we develop a knowledge-driven driver assist agent based on large language model. Our developed agent can work as a driver assist expert that provide insights into the personalized configuration of warnings based on driver need, and also detect hazards from the traffic environment, generate the personalized driver assistance contents to one driver. Of course, these limitations need further improvement, and our future work will focus on improving the accuracy and efficiency of language models through fine-tuning. And also, we hope to conduct human-centric evaluations such as questionnaire and driving simulation experiment to test the influence of the system on the people's driving behavior. And also we hope to develop systems for driver behavior monitoring and behavior reflections. Thank you for your attention. In fact, we are very interested in the advanced large language model methods and their applications in the human-machine interaction of autonomous vehicle. So welcome to connection and collaboration. Please feel free to reach out if you want further discussions. Thank you.
The button for the audience. Yes.
Please.
Go ahead. Mentioned we rank the hazards based on real names or based on what? The vision language model will generate. It just lists the elements in the traffic environment, and the large language model will rank the hazard according to their level of urgency. Thank you.
And
I have a quick question regarding the different driver type.
Okay.
Is there any overlap among those driver types? Because a foreign driver can be also a novice driver, right? So how do you consider the types and how many types in total? Do you only have 3 or you have multiple types?
Yeah. In the first stage of evaluation, we use large language model to generate maybe 3 types of drivers with unique characteristic. But in the later evaluation, in fact, we collect realistic driver profiles from questionnaire. From realistic, they have complex, as you said, they have complex factors. They are not only old driver, they may also have other features. These drivers, the profiles demonstrated in the slide is only for demonstration. In fact, that driver, yes, as you said, drivers may have different features and the system will analyze their different features. Thank you.
Good. All right. Let's take all the time. Thank you. So our next talk will be from online, from Joey Tai, from University of Washington. Joey, you can try to share your screen if it's available, and I'll try to pull this one.
Yeah, sure. Thank you. Okay. Sorry. Right. Can you see that?
Just yeah, give us 1 sec. I'm setting up the system right here. Can you speak one more time?
Oh, yeah. Can you see my screen now?
Yes, we can see your screen and we can hear you. Yeah, you can go ahead.
Okay, thank you. Thank you so much. So before I start, first of all, thank you all the organizers for this workshop. It's a great honor for me to share ideas and insights here and learn from everyone here. I cannot join you here in Edmonton in person due to visa issues, and that's such a pity. So now I will share this research work on behalf of all authors in the paper via Zoom. Let me start with the background. Nowadays, many factors, including constantly growing populations and rising car ownership, aging transportation networks, they're all increasing traffic congestions and reducing mobility efficiency significantly. Especially after pandemic, people are accustomed to drive their own cars rather than taking public transit for commutes and travel, which causes large burden to traffic systems. And as reported by Washington DOT, an intensive vehicle travel volume is observed, and the annual VMT of the state highway of King County reached a total of 8.5 billion in 2022, and its number kept increasing in past 2 years after pandemic recovery. So with the digitization of traffic sensing infrastructure right now, like traffic detectors and sensors all around the network, an immense amount of traffic data is being generated based on this large traffic volume. And this creates challenges in its analysis and further real-time monitoring and management. So these data are often stored in large-scale databases, and based on different data collection methods, these databases have many features with complex relations, tremendous data volume, and multiple tables. Traditional statistical methods and machine learning methods can be used to dig patterns in numerical data, and these tools and methods all have weaknesses that draw people's attention. Like we list them here, there are 4 of them. So first, they require deep understanding in database and process and deep understanding in like data science, at least processing the data and analyze the data. Then second, they are labor intensive and time consuming. Third, they not only need database experts, but also those who have in-depth domain knowledge in transportation and traffic. In actual practices, traffic data is often inaccessible due to privacy issues, right? Limiting its use in daily transportation planning and management. So is there any solutions? This brings up our research objective. So the motivation, the rise of LLM itself is one strong motivation. And in addition, many researchers are now exploring what kind of contribution LLM can make in the field of like traffic management. We can see that like signal control, forecasting, and even autonomous driving, etc. There are problems that they are able to solve or at least give some help to. However, what falls short is the research that focuses on the analysis of real-time traffic performance. Therefore, we hope that this study can achieve the following goals. This TP-GPT should be interactive. It can take in users' questions and complex tasks and give analysis results. And its intelligence should also focus on querying real-time big data and wide pre-trained professional knowledge base. It should also be privacy preserving and provide practitioners and researchers with insights into authorized data in a secured way. And it must give responsive, detailed, and trustworthy and accurate responses into to those input questions. However, deploy LLM directly into the database can cause many problems. Contextual knowledge is essential to avoid hallucination, and the sequential commands execution without iterative, let's say, iterative refinements leads to unpredictable answers. So we develop our methodology while ensuring these issues are addressed. Our database, first, let's say, our database it uses loop detector data from the greater Seattle area. And this database has tables for definition and loop data and performance score data. They cover the 7 major freeways in the area, in the King County, I think, around Seattle, and are updated in real time with an update interval of 1 minute in a total size of like around 2 terabytes. And this is the overall system design of the proposed mobility analysis chatbot here in our research. So first, we have a question or task as the input. And after this question is input, the task scheduling module, the first one, it deconstructs the original complex task into subtasks by understanding what users need and assign them to the query generation module. The system uses generative intelligence of LLM to code SQL queries accordingly, right? Then the system checks the quality of queries to see if any errors existing in the query. And then the target data are sent to analysis module to give a natural language traffic analysis report, the result, based on their pre-trained domain knowledge and reasoning abilities. Right. Besides that, we also conduct a multi-agent strategy. There are 4 agents. So the first management agent it controls the whole workflow, influence the next action based on the execution result, and the next quality agent checks if syntax error exists or query data is wrong or not, and refine the query, and refine the input, and SQL agents understand the input demands and generate SQL queries for desired data. Analysis agent, the last one, also you can see in the last module of that system design, it creates mobility analysis report on target data based on domain knowledge. Right. Another part is prompt engineering. This is designed to interact with LLM in these parts So the first one, preliminary contextual information like basic setup of database, and initialize those agents by telling them their tasks for each role, also giving domain knowledge to make sure they provide professional results. Then there is a future learning prompt. Let's take a look of what it is look like in our work here, right? In actual scenarios, the model may receive multiple similar tasks. So therefore, this is important to enable them to draw inferences from one example to another. And the core of this part, the future learning part, is to search case similar questions in our example list, and I'll talk about that later, and populate the prompt with extracted example, then combine the prompt with the initial question, the user's question, and input to the model. So here's the experiment section. In this experiment section, we created a benchmark based on our own experience and that of industry experts. It covers spatial temporal traffic condition inquiry, pattern recognition in traffic, peak traffic behavior analysis, and etc. A lot of aspects in traffic, like analysis and management area. It consists of 50 traffic inquiry and advisory question query pairs in real-world scenarios. Also, there are 3 levels of results set as the metric, like non-functional, imperfect, and flawless. Note that this is not, these 3 levels, this is not mathematical metrics. We actually, here we evaluate the results based on human experts' feedback. And then we calculate the rating score using results level. And this is actually the math part. That's the math metrics here. Here's some comparison with baselines. It is our model, TP-GPT. It is tested against several popular and strong models like GPT-4 Turbo, PaLM2, and SQL Coder. We can see that it outperformed all baseline models here, with an average score of 0.87 on transquery. That's our benchmark. So in 80% of the tasks flawlessly. And baseline models like GPT-4 Turbo scored, 0.57, and solving only 44% of tasks flawlessly, while PaLM2 and SQL Coder lagged further behind. Yeah. And yeah, so its performance is great, and it was attributed to our multi-agent strategy, error checking mechanism, and future learning capabilities. So we compare its performance of variations to validate the effectiveness of each module. Right. The result here, it shows that the prompt contributes the most in our TP-GPT. Yeah. Without the prompt, the model performance lowered a huge level. Right. Oh, right. Almost forgot. We also have interactive type of web application, but I think you can access to that in our paper. Right. Yeah. So this is basically our work. We developed this TP-GPT leveraging real-time traffic data and LLMs to help people in like transportation management, like traffic analysis, and it combines several modules and validated on a challenging traffic analysis benchmark transquery and performed well. That gives us confidence to believe its effectiveness in resolving complex real-world tasks in transportation management, resolving inquiry tasks. We also thought of some possible future directions, such as enabling the system to locate the specific destination, potentially by embedding map recognition, right? And or integrate toolkit function into TP-GPT. Maybe empower it with ability of handling forecasting tasks or like data imputation, etc. And thank you, and I'm open to all the questions. Right, here's some appendix that you might be interested in. This is some sample questions in our benchmark transquery. Like the left bar are the question types, and the details question are here. So, yeah. Thank you.
Yeah, thank you, Joey. We have a question from an online audience. I think you can probably read that as well, but
Yeah.
I'm gonna read it for you. He has a question regarding the privacy. Will you directly send your traffic data and prompt to the LLM, for example, ChatGPT? And if so, he believes the ChatGPT will use your data to improve their model. How can privacy be guaranteed in this case?
Right, thank you. Yeah, I see that. Thank you for the feedback. And this is a great question. Actually, our model is it's a local model. We deployed this model in our local environment, so we don't we do not upload all those private data to the online ChatGPT. Yeah.
Yeah, so everything's offline, right?
Yeah, everything is offline.
Okay. And Joey, another question that I might have is regarding your few shot learning. I'm just curious, how many examples do you fit into the chatbot for the few shot learning example?
Yeah, great. That's also a great question. Okay, you get back to the future learning part. Right. Like in our benchmark, we usually have 3 to 4, 5 examples here in each category. Right. I hope that answers your question.
Yeah.
Okay. Yeah, I wish I could answer your question in more extensive details, but I think actually this part I'm not able to give a precise and comprehensive question right now.
Sure. Yeah. Thank you. Thank you, Joey. And we have a question from one of another audience. Yeah.
I see the performance of the SQL rendering correct working queries, but what about the time performance of the generated SQL regarding to perform on the difference? Is there any consideration?
Probably it's easier if you can just come to stage. Yeah, because if I reiterate, then I might miscommunicate.
Yeah. So like.
Yeah, if you can directly speak to the mic so we can hear.
Yeah, I have a question regarding like for the SQL query. I see the performance of the rendering correct query that get a desired result, but queries can vary the time performance. So have you ever test on that part? That's my question.
Yeah, thank you for the question. Let me just make sure. What you're asking is like, have we tested SQL query on time what?
Yeah. The like you say you have a very large database, so I wonder like different queries can result in different time performance to get a result. So yeah.
Oh yes. I think we have not yet tested the time effectiveness of the model of the query, but in our case, most of the questions should be there should be answers in at most 2 minutes. Yeah.
Oh, okay. All right.
Yeah.
Thank you.
Thank you.
Okay. Thank you, Joey. Let's thank the speaker one more time. Thank you very much.
Thank you.
So next speaker is going to be myself. Actually, I'm going to speak on behalf of my student who cannot be here in person. So let me start to share my screen. Share sound. All right, so for the next 10 minutes or so, I'm gonna probably cut to the chase and show our demo directly without introducing too much of the details. because I think all the other speakers have already elaborated a lot on what's LM, what's the usage for personalization, for autonomous driving, and things like that. So again, my name is Azir Wan. I'm assistant professor at Purdue University, and this work was actually done last year, end of last year, December, and we did a field experiment, one of the first, if it's not the first, field experiment for human autonomy teaming using large language models. Probably just to lay the background a little bit, why do we want to focus on personalized autonomous driving? I have been working on this field for 7, 8 years. Before I joined Purdue, I worked for Toyota, and I led one of their personalized autonomous driving projects. And to personalize specifically adaptive cruise control feature on the vehicle. For those of you who are not very familiar with adaptive cruise control, so essentially you can press the button on your vehicle steering wheel to adjust the gap setting to follow your preceding vehicle. And we a lot of times had a lot of complaints from the users say, hey, this should be autonomous system. I don't want to change the settings every time when there's a vehicle try to cut in, or when the weather changes, or when the road condition changes. We actually did a survey to all the users, and the survey results show that a lot of drivers, they change the settings during one trip, and might be a little bit hard to see, but there are many factors: traffic condition, weather condition, even the mood of different drivers will affect their status of say, especially for car quality. So that was one of the work that we did for personalization for autonomous driving, where we want to collect the data from the users based on the human autonomy teaming process, right? Based on the human computer interaction. Say we collect the data from naturalistic driving. So you drive in the morning, you generate a lot of data for car following. We sample the data, we send it to the cloud, where we have different classification type, like your driver type, your vehicle type, weather type, and road type, and things like that. And we apply offline machine learning models. In this case, there are multiple models we developed, inverse reinforcement learning, Gaussian processing. And the most important thing is next time we switch on the system will learn all your previous preferences and will adjust the settings for you based on the data that you generated in the morning. And this can be, this cloud architecture can be extended to different drivers, can be extended to different vehicles, can be extended to different time zone, time horizon. It doesn't have to be within one day, but as long as you have this cloud architecture and based on the human autonomy teaming data, we can personalize autonomous driving for you. So that was one of the background work. I'm gonna probably show this a little bit. We play simulation, we build in Unity and allow different drivers to interact, collect a lot of data, and then personalize the things for autonomous driving. Another background work is we also did personalized lane change prediction, which this doesn't play, but the key concept is we want to also learn from drivers' lane change data, and then predict different drivers, their possibility of conducting a lane change. What's the percentage? What's the time horizon? 2 seconds later, there is a 85% of the driver will conduct a left lane change. So you better watch out. So those are two of the fundamental work that we have built for cloud-based personalized autonomous driving, and that leads to our work in LLMs. So we're not just using LLMs for end-to-end autonomous driving or just replacing any of the modules on the vehicle, but we want to use LLMs to help, as I said, the human autonomy teaming process, to help our autonomous system to better understand the needs from the human drivers and passengers in the future, and better satisfy their preferences and make our system more preferable for those passengers in the future. If we're talking about level 4, level 5 vehicles, there's no drivers anymore. So how can our vehicles satisfy their needs? So that's our niche. That's the thing that we're focusing on. As I said, I'm going to cut to the chase. LLMs, everyone knows about it. It can understand the implicit needs from different humans, taking this last one as example, say if one human passenger says the rush hour is approaching, probably one means you need to be as quick as possible to avoid traffic. So this is a more aggressive passenger or driver per se. But the other person might mean you need to be careful as the traffic will be complex. So saying the same sentence, they might mean different things. Probably for traditional language processing system based on NLP, it might be hard to understand. But using large language models, we can understand the whole context. We can use in-context learning, chain-of-thought prompting to help our vehicle to better understand what this human being, this human passenger really needs, and how I can adjust my settings. There are different systems out there. Some people use it for perception, some people use it for control. We specifically, for this research, we use LLM for decision-making. We personalize decision-making for autonomous driving. Of course, we identify there are limitations like hallucination, like real-time inference, because we're leveraging the cloud architecture. We send everything to the cloud. We leverage OpenAI's ChatGPT or GPT-4 API. So there is a noticeable end-to-end latency from vehicle to cloud to vehicle. Again, you can find this in our paper. So I don't need to go through the detail of this figure, but again, we send everything to the cloud. It's not a offline version, as Joey mentioned in their talk earlier. But in our case, everything is on the cloud. We leverage OpenAI's API. We send a query to the API, and we get the feedback from it. So it takes some time. And if you look at the diagram on the right, we will first switch on the system by saying command. It's like, hey, Alexa, hey, Siri. And then we'll allow the human passenger to provide information to the system. But the green part is also a novelty of our work, where we provide feedback to the system. And we store all this feedback, the interaction between the human and the autonomous system in the memory module. And the memory module, the historical data will be then concatenated to the real-time data and sent to LLMs for future inference. So this is our setup. Again, I said we were probably one of the first groups to do the real-world experiment demo on real autonomous vehicle for control in the loop system. It's not just scene understanding, but we tap into the control model and allow our LLMs, decision maker, to interact with the control model. We have tested 3 different scenarios. The parking scenario is we allow our autonomous vehicle to select the preferred parking spot. The intersection scenario is there is an unprotected left turn where you have vehicles coming from the other lane of the road. And also highway scenario, our vehicles driving on a 3-lane highway. And we showcase 2 trips per scenario. One is without human feedback, and one is with human feedback or with the memory module. This is our test vehicle. It's a drive-by-wire control enabled vehicle, so we can tap into the control module. We can change the speed of the vehicle, change the acceleration, deceleration, and steering input of the vehicle. Here is the experimental track that we did the experiments. The first 2, the highway interaction and intersection, we did it at a airport runway. It's no longer in use, so we use it for our testing purpose. The parking lot scenario, we tested at our Purdue campus. It's a giant parking lot. So I'm gonna play this video and you'll see what I'm talking about. So first is parking scenario, where we need to find the parking lot based on the implicit command from the passenger. Again, you don't have to say, find that parking lot next to that vehicle.
Command. The game is about to begin. I don't want to be late.
But just this kind of implicit thing, I don't want to be late. I want to catch the game. And you can see the prompting of an original process of LLMs, right? The driver is in a hurry to catch a game, so I should park near the stadium as soon as possible. So the LMs make the decision of, I'm gonna find the closest parking space to the football stadium. And the vehicle goes, navigate through the big parking lot, trying to find that parking space that's closest to the football stadium. At the end of this trip, the passenger provides another feedback to the system because he was not really happy about it.
Evaluate. Even though I'm in a hurry, next time you can park near the exit in order to avoid traffic when I leave.
So the passenger figured out if I park too close to the stadium, then it will take me forever to exit the parking lot after the game is finished, right? You have thousands of cars trying to exit at the same time. So next time,
Command. The game will begin in 5 minutes.
he said something similar. The game is about to begin in 5 minutes. You can see the thought by LMs. This time I should park near the exit based on the memory module, based on the previous feedback from this passenger. And then here he goes. The vehicle found the closest parking lot to the exit. And then another feedback from the passenger.
Evaluate. I'm satisfied with this trip.
So he was happy about it. The second scenario is intersection, where we have unprotected left turn scenario.
Command. I'm on my way to the emergency.
So he said he's on the way to emergency, and I think LM's reason that I need to drive as fast as possible while ensuring safety. So as I said, this is an unprotected left turn where you have vehicles coming across from the other side of the road, and LM decided to turn left before the other vehicle cross. It looks a little bit risky, and then the passenger provided his feedback.
Evaluate. Even though sometimes I'm in a hurry, next time you should still wait for the opposite vehicle to pass.
So he wanted to still be a little bit safer and provide feedback to LMs, so LMs can do the in-context learning and then this time react differently. Again, implicit comment, I'll be late for meetings, but in this case, LMs knows about it, consider about the safety. If you look at the reasoning process, so we need to speed up, but also wait for the opposite vehicle to pass. If there's any, right? In this case, it is. There is a vehicle pass from the other side of the lane again. And then this time, LM decides to stop the vehicle there.
Let's continue turning when it's clear.
Another feedback from the passenger, let's continue turning after the traffic is clear. And then our perception module on the vehicle sense, okay, the scene is clear, and then LM decides to make this left turn after that vehicle is cleared.
Evaluate.
Another feedback.
I'm satisfied with this trip.
Satisfied with this trip. And again, this console window on the upper right corner, it might be a little bit hard to see the details, but the messages means the real-time communication between the vehicle and the cloud API. And in this specific scenario, there were 3 iterations, right? One from the very beginning. Second is for the passenger to tell the vehicle to turn left after the traffic is clear. And the third one is the final feedback, 3 iterations. The last one is highway scenario. As I said, there is a 3-lane highway, and there's a aggressive driver in front of our Ego vehicle who drives like zigzag kind of thing.
The front vehicle looks weird.
And that's the power of LM. You don't have to tell, I want to change the lane to the right, decrease my speed from 40 to 20 in 10 seconds or so. You just said the front vehicle looks weird, and that's a decision made by LM.
Evaluate. Next time, please directly overtake the front vehicle.
The passenger was not happy because he thought it was too conservative. Let's just overtake, right? And this time, similar command, but different decision.
The front vehicle looks very crazy.
LLMs figured that out and then decided to do a quick and clear left lane change, speed up, and overtake that vehicle.
Evaluate. I'm satisfied with
And you
this
can
trip.
evaluate, you can provide feedback on the fly to LMs, and then provide further context for future inference. And I may just skip all those results, but jump to the conclusion. In this case, as I said, we are leveraging the cloud API, so the latency is noticeable. It's 1.2 to 1.8 seconds end to end, which means there's no way for you to do very time critical real-time control of the vehicle. But that's why we use it for personalization, for decision-making process, to choose the route, to tune the parameters for your, say, control modules and things like that. And it's not like highly frequent at 10 hertz or something. It's just every, say, 10 seconds or even longer, you just have one iteration or two. And we use it, as I said, as a niche point to use it for personalization. So we didn't replace the whole modular architecture with LLMs. We actually empower our modular systems with LLMs instead of replacing all that. You know, we showcase the safety and comfort advantage in our paper, but I'm gonna skip. We have been, our lab has been doing this kind of research for quite some while, starting from last year. And we have made a lot of different work. Field experiment is just one of them. We published a benchmark data set. We did quite several simulation work and you know, published papers on CVPR, WCV. So we have this website for everyone who is interested to follow. And again, just presenting on behalf of my students. My student Ken Hui was the one who lead all this work experiment with Zichong Yang and Yupeng Zhou. And Yunshen was the one who led the theoretical work of this. And we also have several other professors who were part of the team. Okay, that concludes my talk. I'm happy to take any questions. Yeah.
So thank you for your impressive work and presentation. I have one question. How you consider the situation? Sometimes the passenger may give harmful information. For example, let the vehicle to crush pedestrians. How you consider these situations? Will the large language model perform such tasks, and how to prevent the large language model from performing this task? And whether do you think it's a problem also related to cybersecurity?
Yeah, it's a great question. So that's why, as I said, another background of this is that this work was founded by Toyota, which I worked before. And you know, from the OEM's perspective, they definitely don't want to replace the whole modular system with LLMs, right? Which they consider as a black box. So that's why the way that we did it is we add LLMs as an additional layer to our decision making or planner, and we have our control model, we have our safety filter added last to keep monitoring the output of LLMs. If LLM's output falls outside of the safety boundary of our system, say if LLMs suggest, based on the human input, LLM suggests something that will be causing potential risk, will be causing potential collision. We keep monitoring the time to collision value and things like that. Then we just kick LLM out. We have the right and of course the authority to keep LLM out of the loop at any time, as long as soon as we figured out the output of LLMs is malicious. So it's just additional layer, and we have a parallel system, Ruby system, to keep monitoring the output of LLMs. If it's good, then of course we will use it. But if it causes any potential risk, we will just kick it out. If that makes sense. Any other question? Yeah, go ahead.
How do you translate LLM text to actions?
Yeah. So we use code as policy, and of course we fit examples to LMs. Say here is the context, here is some vehicles that you want to overtake, and here are some trajectories you can pick. And then LMs will say, in this case, just output a certain trajectory number for our vehicles to pick, and then our planner and controller will choose that. Some other examples is we use LMs to tune the parameters of our MPC controller. So the output of MPC of LM will be the specific values of, say, the prediction horizon of the MPC algorithm, and then just some numbers. So yeah, we use Godot's policy, we use in-context learning to tell LM, here's the input, here's the output format, and then we directly use the output format of use the outputs from LM to our systems. Yeah. If we don't have any more questions, then we can switch to the next talk. Thank you.
Hi,
yeah, go ahead.
Yeah, I think I tried to send my question to the chat box, but it seems like
yeah, because I'm presenting and I'm moderating, so it's hard to see. Let's see. So you have this question for model agnostic to speaker accent. Oh, that's a great question. Safe and responsible AI is a thing. So probably the thing that I didn't mention is we actually use the API called Whisper API to first transfer the audio to text, and then use that text to feed into LMs. So to answer your question, I think it's agnostic as long as it works for that Whisper API. It's an open source API to transfer your audio input to text. And in our system, we don't really care about what accent. It can be even in, say, the drivers can speak in, say, Chinese or in Korean or in any other language, as long as that API can transfer that into a certain context for LMs to consider. So if that answers your question.
Yeah, thank you. So the other part of the question was like, if you consider a traffic scenario during the testing, because I was just wondering, like, interaction with other vehicles, interaction with human. Like, I was just like wondering, or if it wasn't considered, do you actually like plan to consider that in the future?
Yes, it's definitely part of our future plan to consider that. Actually, I think one of our work already considered that. I'm gonna share with you more details after this talk. Okay. Probably it's a longer answer, but thank you for the question.
All right, thank you.
Yeah. Okay, let's switch to the next talk from UC Santa Cruz. Ishan, I think you are online, right?
Yeah, I'm here.
Yeah, if you can go ahead and share your screen, that would be great. And Ishan's talk is going to be on scenario QA, evaluating test scenario reasoning capabilities of large language models. You can go ahead and get started.
Okay, thank you for inviting me to this workshop and for the opportunity to present our work. Unfortunately, I could not be there in person. So I'll be making the presentation here on Zoom. So so autonomous vehicles need to be rigorously tested before they are deployed in the real world, and generally testing has two complementary types of testing, which is simulation-based and real-world testing. Simulation-based testing offers low-cost approach for creating situations or scenarios which cannot be created in the real world, such as dangerous situations. So we need to design complex and high-quality tests to effectively test autonomous vehicles. And there need to be a large number of these test scenarios, and automated methods can help a lot. So large language models have presented us with a major leap forward in the natural language generation systems. However, its complete range of capabilities, especially in the design of the autonomous vehicle test scenarios, remains unknown. So we have created Scenario QA, where we present an approach to design a QA benchmark to evaluate LLM capabilities for scenario reasoning. So on the left here, I've just shown how complex a scene is for an autonomous vehicle. And if an LLM can describe such a scene, it can help with the generation process of these test scenarios. So a scenario is in the research literature is defined as the temporal development between several scenes in a sequence of scenes. So a scene is defined as a snapshot of the environment, which includes the scenery and the dynamic elements, as well as the actors and observers, and the relationship among those entities. So in scenario-based testing, we are attempting to make an assessment of safety based on the performance of the vehicle responding to certain scenarios. And there are many ways to define scenarios in the research literature. So there's the functional, logical, and concrete scenarios based on how the description has happened. So the functional scenario would be a verbal description, logical scenario would have parameter ranges, and concrete scenarios would have specific parameter values. There are other models described as well for scenarios, such as the 6-layer model based on the elements that are present in a scenario, the static elements such as the road, and the dynamic elements such as the vehicles and the pedestrians and their behaviors. And so recently, large language models have been used for autonomous vehicles. So we did see the presentation from Long about Wave's autonomous vehicles and how they're using vision models. So one vision model is the Lingo 2. And one issue here is that when we're using LLMs for autonomous vehicles, they struggle to reason about the scene that is presented to them. And especially they struggle to reason when there are multiple frames provided and there is some kind of dynamics happening across those frames. So this other paper that I've cited over here does this evaluation, and they find out that LLMs have issues detecting the direction of movement of other traffic participants, detecting the acceleration and deceleration of other participants. And there are a lot of biases in the training data. So for example, the training data for these vision models has a lot of vehicles moving in the forward direction. So if you present an input where there is a vehicle that is reversing, it might have difficulties in understanding that motion. LLMs have also been used for the test scenario generation, but generally they make use of other tools and just provide a few inputs to those tools. So I've cited 2 papers over here which make use of a tool such as the Sumo traffic simulator tool, where the LLM provides some description of a road and description of the vehicle routes, but the Sumo simulator does the verification step and provides the errors or any kind of feedback. And in this other paper, there is the evolutionary search is used for generating scenarios, and LLMs just provides some kind of assistance, such as the setting up the initial population or in making sure that the algorithm does not stay at a local or maximum. So one takeaway here is that the large language models are still not used for the complete scenario generation process. And this might be because the scenarios are very complicated and a lot of reasoning is required for the scenarios to be consistent. So we have designed the scenario QA approach, where we modify and extend several LLM QA reasoning benchmarks that are relevant for the domain of scenario reasoning. We present an approach to design these multiple choice questions and then have them be generated by the LLMs. And then we also provide an approach to evaluate the pre-trained LLMs. So by pre-trained LLMs, what I mean are these large language models which can be contacted through an API, such as the GPT-4 or the Cohere models. So for evaluating an LLM capability, we generally make use of these QA benchmarks. In QA benchmarks, we create these question answer pairs. Generally, they are multiple choice questions. so that the calculation of the final accuracy score becomes much simpler. So one example of this is common sense QA. But in the domain of autonomous driving, there are other benchmarks as well, such as the MAP LM QA or the new scenes QA, but they are focused on visual understanding and not necessarily the reasoning or the relation between the semantics, such as in temporal reasoning, there's the concept of before and after. In spatial reasoning, there's the concept of near and far away. And so that kind of evaluation in the QA datasets is not present. So we hope that this scenario QA process captures that. So yeah, I've already described this, that in scenarios, there are many different moving parts. There are static components, such as the road geometry, the environment that is provided, the different objects and the road signs that are present. There are many dynamic components, such as the vehicles, the pedestrians. And so to consistently create a scenario that captures all of this across time, there is a lot of reasoning that is required. So to design the questions in this data set, we modify and combine several approaches. So we take a structure for the multiple choice question generation, a structure for the different scenario related concepts, a structure for defining what reasoning is and what a reasoning style is. And there are other minor parameters which are all of this is combined and put into the LLM question generation prompt. And that from there, a set of like QA pairs are generated by the LLM, which we can use for scaling up and creating a large data set. So for reasoning specific question structure, we made use of several benchmarks that we believe were relevant for the domain of test scenarios. So we made use of the common sense QA, the entailment bank, and the SPART QA. Common sense QA provides us with certain concepts from the concept net domain, and reasoning here is defined as certain relations between the concepts. So this is one example of the questions that are generated within the scenario QA approach. So you might see the second word over here, which is causes. So one of the reasoning definitions in common sense QA was the cause and effect relationship between certain given concepts. And so that is provided within the prompt to the LLM for the generation of these questions. And then with Spark QA, we have certain spatial relationships, such as what is near, what is far away. So all of that is defined as a reasoning style, and examples of these reasoning style are entered into the LLM prompt, and so that it can carry out the in-context learning and understand what that reasoning style is. In addition to the reasoning style definitions and the examples, we have also created the multiple choice question structure. And within this question structure, the multiple choice question is defined as a question where there is one correct answer and many incorrect answers. The correct answer is the stem. Incorrect answers are the distractors. And within that, also the distractor needs to be quite close to the correct answer. And along with that, based on this paper, we also make use of the Bloom's taxonomy concepts, since multiple choice questions are designed to evaluate certain types of learning within the people. And so those kinds of learning can also be evaluated, can also be entered into the MCQ structure in the LLM prompt. So the first word tag here you can see as understand, and the first word tag here you can see as apply. So those are the Bloom's taxonomy concepts. There are I think 6 to 8 concepts, and so along with the MCQ definition, we can also ask it to address some of the Bloom's taxonomy concepts while generating these questions. Another parameter you might see here is the 1 hop and the 2 hops. So this is similar to one approach used in the new scenes QA, where the reasoning does not happen just once to answer the question. The reasoning process is followed multiple times. And so that can help us create more complex questions and more difficult questions. Along with all of these structures that are provided for the generation of these questions, we also need some concepts which are relevant to the test scenarios. So for this, we make use of the ASAM OpenX ontology standard. These are the standardized data formats which are used for autonomous vehicle test scenarios. So OpenX involves road formats such as OpenDrive, scenario formats such as OpenScenario. And so within that, there is the OpenX ontology standard, and it involves many different concepts. So one very small example here, which is used, is the vehicle communication activity and the flashing headlights. And so we provide, along with the different structures for MCQ generation, structure for the reasoning style, we also provide these concepts and ask the LLM to make use of these concepts when it is generating those questions. And then finally, once the questions are ready, we make use of the Light LLM library to prompt multiple LLMs at the same time to check its responses. So here you can see the interface where there is the prompt is provided, and then all of these LLMs are evaluated. So in our experimental setup, we wanted to generate effective questions. And so we wanted to see which parameters will affect the effective question generation. So the wording, so all of these parameters were varied across the experiment runs. And so the wording of the question examples was important. The ordering of the information, some of the examples were removed, and then the final generation was checked. The reasoning type being used, the examples, the number of the examples that are provided, the reasoning hops involved, the LLMs, the consistency across separate chat contexts. So since the generation of the LLM is not completely deterministic, we wanted to make sure that how similar the generation was for the same prompt across different chat contexts, the number of iterations in a single chat context, and the explanation generation. Regarding the final evaluation for the given questions, we can just measure the accuracy score. So the question generation did make use of the concepts which were provided from the given ontology. The LLM was able to capture the reasoning style which was given in the different examples. The more the number of examples, the better it was. Not adding relevant incorrect answer choices also reduced the question generation. So this would be examples where a lot of the multiple choices were just random words and not relevant to the question that was being asked. So that also affected the generation. Combining reasoning examples with Bloom's taxonomy terms improved the reasoning depth. Simply mentioning reasoning hops and asking it to generate complex questions was not very effective, but actually showing that in the in-context examples was more effective. There was one issue with redundancy. So when several questions were to be generated by the LLMs, a lot of the subsequent questions would involve the answers for the previous questions. And so the temperature parameter was quite crucial over here. And in addition to that, we can also provide a per question structure. And also increased temperature parameter affects the reproducibility of the prompt output. And so this is something that would probably need to be balanced. Mostly the final questions which are generated, the LLMs got a very high accuracy. And so there might be an issue here where the questions need to be a little bit more complex. And so we will be addressing that in the future work. And also in the future work, we want to evaluate the vision language models and design questions for. So that's my talk. Thank you. Thank you for organizing this.
Yeah, let's thank the speaker.
Thank you.
Any question from the audience person? Looks like there is one in the chat. Okay, that's not. Okay, thank you, Ishan. Since we're running out of time, so I'm gonna let you go right now. But if we have more questions, we'll follow up in the chat. But thank you for attending online. Thank you, Ishan.
Okay, thank you. Thank you.
So the next speaker will be Yun Li from University of Tokyo, who will talk about large language models for human-like autonomous driving, a survey. Will you use mine or use yours? Yeah. Yeah, I think. Have you logged into Zoom?
Oh, no, sorry.
Not yet?
So I should log into.
Yeah, you have to share your screen. Yeah, I think they just send out an email to you, the Zoom link.
Sorry.
Okay.
Okay. Hello, everyone. I'm very honored to have a presentation here. And my name is Yun Li, and I'm a first-year PhD student from the University of Tokyo. And today, my topic is about large language model for autonomous driving, and my work is a survey paper. Well, first, let's talk about the background of LLMs and multimodal LLMs. And the researcher in Google has found that with the increase of parameter size of AI models, there is an interesting pattern that the AI model can have the ability to solve different tasks like language understanding, translation, and code compilation, and so on. And such a good performance may have the potential to be used in autonomous driving, such as it is knowledge-based, it has world knowledge, and such a knowledge may be helpful for the decision-making for autonomous vehicles. And it can process natural language instructions which means the autonomous vehicle may have the potential to understand the instruction of human directly. And next, it has a few short learning or zero-shot learning abilities and transfer learning abilities to solve the problem of corner cases in autonomous driving. And we can see from 2019, since Google has proposed its first T5 LLM model, and there are more and more LLM models being proposed, like publicly open sourced or not open sourced, like GPT or open source Llama 2, Llama 3. Yes, so we can say that LLM is a popular research direction, and more and more researchers has concentrated on the development of LLMs. And I think the LLM can be represented, the function of this can be represented as here. Here the X is its input, which is a paragraph. It is composed of several sentences, and each sentence is composed of several tokens. And the output of LLM of F is a probability distribution over the next tokens, which means given the previous tokens, LLM will output the probability distribution. For multimodal LLMs, the input X is not is not just text. It can be other modalities like images, videos, or sounds. To further understand the multimodal LLMs, I think this is a good reference. In autonomous driving vehicles, the vehicle should face different modality from the environment. And in this paper, the researchers has tried to combine these modalities like images, videos, text, audio, depth, thermal, and IMU data into a unified models. So LLM can understand the complex environment. And there are so many works in the autonomous driving community, but I think most of them is based on this framework, which is a vision language action model framework proposed by Google. It's called PaLM-E, and the inputs we can see there are embedding from the environment, and the images and the question from the human users, and via different encoders, and we get the unified tokens, and the LLM, they use PaLM, can process these tokens and output tokens. These tokens via decoder, we can get the answer to the question and the control command to the robots. Although it is used for robots, many researchers has referred it to be used in the autonomous driving area. Well, as for the evolution of autonomous driving systems, conventionally, we have rule-based and optimization-based autonomous driving. For rule-based AD, it uses a rule engine, like if we meet one condition and we take the action. Yes, this is simple, but the autonomous driving task is very complex. So it's impossible to define every rule for the real environment. And optimization-based autonomous driving, they use mathematical optimization for the decision-making process, like MPC, MIP. they solve the constraint optimization problem. But if the constraint problem is complex, it will maybe impossible to solve, and the latency is unacceptable, I think. And in the second stage, with the development of deep learning techniques, there are so many learning-based autonomous driving techniques, like reinforcement learning or computer vision. They learn the pattern from the same inputs and get output via the map of the neural networks. And in the third phase, I think, with the popularity of LLMs, we have the knowledge-based autonomous driving. It's based on the knowledge of LLM. We can have the potential to get over the long tail scenarios and achieve human-like decision making. Yes, via the prompt. Yes, the first part is about the modular decision making in autonomous driving. And it's about the integration of LLMs with traditional AD tags. The inputs, maybe images or sensor data from the upper layers, like sensory or perception layers. And the function F will output the module-specific actions or intermediate results. And the LLMs will be, first we have the pre-trained LLMs, and then we fine-tune it in the domain-specific datasets. Well, here are several previous works, but I don't have time to explain them one by one. But you can see that they combine LLM with MPC or PPO, which is SOTA, reinforcement learning algorithms, and so on. And another field is about end-to-end autonomous driving approaches. And LLM will work in the closed loop evaluation systems. The input is directly from the raw sensor data, like LiDAR, radar, or cameras, and the raw or environment information, and etc. Via the process of this end-to-end system, we can get the direct control commands or high-level driving decisions, and then the low-level driving decisions will be made via MPC or another conventional methods. And here are several works. I just pick up several representative papers. The first is Aeon Drive in CVPR 2024. And you can see that this framework is similar to the model proposed by Google. And they use adapter several. You can see that the LLM and vision encoder has been frozen because the parameter is too large. It's not realistic to fine-tune them in laboratory. But they just use the adapter and Q-former to train this model, but they use 8 A100 GPUs. It is still kind of a hard GPU effort, I think. And this is Stilu, and this is the first LLM-based knowledge-driven autonomous driving framework. And you can see that to mimic the human drivers, they have added the memory and reasoning modules to mimic the human-like driving behaviors. And they get better performance than previous sort of deep reinforcement learning methods. Yes, I think Lava is a famous VLM open source models. And I have tested its performance in my local PC. But you can see that the latency, I think, is kind of unacceptable. It takes around 2.28 seconds. Yes. And so maybe 5.2 and recently 5.3 has been open sourced. It just takes just 0.17 seconds to output 10 tokens on my local PC. So this may be more acceptable. And it still has comparable performance than Llama 2, 70 billion in the, I think, in the coding score. So this may be one direction to solve the problem of the latency problem of LLMs. Well, as for the challenges and future directions, as the first is lightweight and efficient LLMs for AD applications, because for the decision making, generally we need the latency should be 100 Hz. And next, I think, is to design multimodal training frameworks, because the autonomous driving vehicle, the environment is multimodal. We have many inputs like images and the sensor inputs. So I think this is also important. And next is about the safety constraints and ethical guidelines. You know, LLMs has a problem of hallucination. We need techniques to make sure its output safety decisions and not violate the ethical guidelines. Yes. And next is to generate human understandable explanations, because several humans are not do not trust the performance of autonomous vehicles. If LM can out-generate human understandable explanations, I think the humans may have better understanding of autonomous vehicles. And then finally is to conduct more closed loop tests of LM-based AD in simulators or real world cars. Yes, so my survey has reviewed the integration of LLMs into knowledge-based AD systems, mainly on the decision-making part. And I'm currently working on the other stages of autonomous driving tasks. It's a survey paper. And we have introduced the key features and training methods of LLMs to analyze how they enhance the performance of autonomous vehicles. And finally, we get the conclusion that LLM-based approaches has superior adaptability to complex autonomous driving scenarios and better generalization to new environments, which may help to surpass human drivers in terms of safety and efficiency. And thanks for your listening.
Any questions regarding the survey work? A quick question: how many papers you surveyed in your work?
Because this is just a conference paper, we just put around 70. Yes, but in our survey paper, we have, in the journal paper, we have surveyed over 200. Yes.
You already submitted a journal version?
Yes. Oh no, we haven't submitted. Yeah.
Is it for the survey, for the journal paper, is also just for decision making, or you also consider perception?
Yeah. Perception control in the whole flow of autonomous driving tasks.
Yeah, sounds good. I look forward to reading that.
Yeah. Yes. Thank you very much.
Okay, let's take this one more time. Thank you. Yeah. We'll introduce our next speaker. Basha Parwara from University of Gothenburg, Sweden. He will talk about evaluating and enhancing trustworthiness of LLMs in persistent testing.
Audio and start share your screen.
Thank you, everyone. And I'm super happy to be here today and talk about one of our recent studies with the title Evaluating and Enhancing Trustworthiness of LLMs in Perception-Related Tasks. So before we move on to talk about evaluating and enhancing the trustworthiness.
Share the desktop instead of sharing the slide. It's not moving forward. Zoom, yeah, and just share your desktop. Yeah, share a screen. Screen 2.
Screen 2, probably, yes.
Yeah, sorry.
Is it talking now?
Yes.
Yeah, okay, perfect. Yes, so before we start talking about the trustworthiness of LLMs, I wanted to start off with this question. So can an LLM support perception-related tasks within a vehicle? And we have listened to a series of talks today, this morning. And now, of course, we know that, yes, we can use LLMs to support perception-related tasks within vehicles. So I wanted to narrow down my research area into pedestrian detection and localization specifically. And as an example, in order to perform this kind of a task using an LLM. So we, as a group of researchers in University of Gothenburg, we showcase that, yes, this can be actually possible. So in fact, the diagram that you see on the screen is a response that generated by LLM. So this can be actually done, and we presented this paper earlier in August in ITSC2024, where we showcase that, yes, we can use LLMs to do the pedestrian detection and localization. So nowadays, we know that there are very advanced driver assisting systems, and also these driver assisting systems are getting more and more advanced day by day. And also these large OEMs like Geely, Toyota, and BMW, they're already working on research where they try to integrate LLMs into these vehicles as inbuilt foundational models. So if we do have this kind of sophisticated vehicles where we have this kind of LLMs inbuilt, we could be using these LLMs for numerous tasks. So first, these LLMs could be acting as human-machine interfaces. And also we could be using these LLMs to generate natural language-based conversations between the in-car passengers and the car itself. So, however, in which way that we use LLMs, we need to make sure that the LLMs are trustworthy, because we are more concerned when it comes to vehicles, which we consider as safety critical systems. We want to make sure that the LLMs are trustworthy and they work as we expect them to work. But the problem is LLMs very often hallucinate. And this has become a very known issue in the domain of LLMs. So hallucinations, they stand for these very specific scenarios where the LLM actually generates some nonsensical or unfaithful information. So the output is not what we actually expect the LLM to generate. So in this study, we wanted to identify the types of hallucinations that we come across when we use LLMs within perception-related tasks for automotive domain. So the first one was false negatives, where the actual image has a pedestrian, but the LLM was unable to detect the pedestrian. And the next type is the vice versa, the opposite, where the actual image did not contain a pedestrian, but the LLM still flagged this image as a frame with pedestrian. So these are the two main types of hallucinations. However, we as a group of researchers, we believe that false negatives are more problematic because there is an actual pedestrian, but the LLM is saying that there is no pedestrian, which could potentially lead to fatal collisions. And not only these two, we also came across with this third type of hallucination where the LLM refused to generate the image. So for us, we don't see anything special in this image, but the LLM obviously saw something that could violate their safety policies. Therefore, they refused to process this image. So these are the three main types of hallucinations we identified in this study. And for the next step, we wanted to find what are the existing hallucination detection and mitigation strategies available. So by the time we conducted this experiment, there were many hallucination detection and mitigation strategies already published, but the problem was majority of these techniques were tackling with text-related inputs. They were not taking this multimodal data input. So the applicability of these techniques into ADAS-AD domain was questionable. So we came across these three techniques: self-check GPT, best of three, and Dreamcatcher. The importance of these three methods were these were adopted into domain of ADAS-AD in with less modifications. So these can be adapted into the domain of automotive. And if you more information has been incorporated in our paper. And yes, so with all this information, we came to our experiment. So we start with the data curation. We picked two main data sets, the Waymo data set, which has been collected in USA, and the Prepper City data set, which has been collected in Sweden, in Gothenburg. So we picked these two data sets, and we wanted to curate a subset, a sub data set, where we specifically wanted to have driving scenarios. So we wanted to have sequences of driving scenarios where multiple frames are visible, and in each of these frames, we wanted the pedestrian to move. So we had a sequence of images where the pedestrian is moving from one frame to another frame. So this is an example of one sequence where we can see 5 frames. And the selected driving scenarios like this, we did some image pre-processing where we removed the horizon of each images, and we split these images into 4 regions. We considered them as left, right, far, and close regions, so that it made the LLM's job easier to detect the pedestrian. And then these modified images as well as the unmodified images, we sent all of these images, we fed them into LLMs. So by the time we did this experiment, GPT-4V was the most advanced proprietary model that was available. And also we wanted to test the open source models as well. So we picked Lava. And then we asked these models whether they can see a human or a part of human visible in this image. And we also restricted the answer into yes or no binary format. So we collected the responses. And at the same time, we asked the same question from a human evaluator, and we collected the ground truth. So now we have these responses and the ground truth collected, and we use these 2 types of data to do our analysis on the collected data. So when we were doing our analysis, first we check the results for unmodified full images. And as many of you can expect, the GPT-4V showed near perfect results. It could detect the pedestrian with great performances, but on the other hand, Lava was not so good. But however, the recall and F1 score for GPT-4V was good, and which showed that we can use these LLMs to do the pedestrian detection. And overall, when we were analyzing our collected data, we found that, as I explained earlier, we had information or data from driving sequences. So we had temporal data and we had semantics over time, and we knew how the pedestrian was moving across the time. So when we were doing the analysis, we found that if we could use this temporal data, we can use it as a hallucination detection mechanism. So with that logic, we proposed this THV method for hallucination detection, where we check the previous 2 frames. And if previous 2 frames contain a pedestrian, then we flag the 3rd frame as a frame with a pedestrian. So this is a proposed hallucination detection mechanism when you have possessed the temporal data. And when we were further analyzing the results, we also identified that we could have done the reverse as well, where we checked 1 frame, and if there is no pedestrian visible, then only we check the 2 previous frames. And if the 2 previous frames contain a pedestrian, then we corrected the response for the Fth frame. So this way, we were able to improve the overall results for Lava by introducing this temporal data related mechanism. But then overall, GPT-4V was better in all these algorithms that we checked, but use of temporal data, it helped to improve the results for Lava. And with that, we also identified the importance of having temporal data. And having temporal data means, like I said, we know the trajectory of the pedestrian. Then we came up with this new hallucination detection mechanism, where we further divided the region of interest into smaller regions of interest. And then if there is no pedestrian visible in a certain region, then we applied THV2 method, and we check the 2 previous frames. But in this approach, we are not only checking that specific region, but we are checking the neighboring regions to see whether there is a physically plausible trajectory. So if it is possible, if the trajectory is possible, then we flag the current ROI as a pedestrian visible region of interest. And by doing this, we were able to improve the GPT-4V results further. So the recall went up to 96.43 and the accuracy went up to 85.86. So all these data are available in our paper. So give it a read, and I'm more happy to talk to you all about the results and get in touch as well. So main takeaways from this study is, yes, we can use LLMs to support perception related tasks within vehicles. But the problem is LLMs very often hallucinate. So we need to make sure that we can detect hallucinations and we can mitigate them, especially when we try to use LLMs within a safety critical domain such as automotive. And the pinnacle of this study is having temporal data on a traffic movement. It helps in identifying hallucinations, and also using the semantic over time, it helps you to detect hallucinations, and it can be a potential hallucination detection mechanism that you can apply in your further research. So as a next step, we also checked whether LLMs can check their own results to detect hallucinations. So as a result, we came up with this study, and it was accepted in ITSC2024 conference, and it will be presented next month in London. So if you are more interested, you can read the preprint from here. And Yes, so these are the contact details of us. This is my research group. So we are very keen on research related to LLMs and automotive domain. So if you would like to collaborate or if you would like to talk to us, just contact one of us. And yeah, that's it, I think. Yeah. Thank you very much.
Thank you.
LLMs, because maybe they have both totally different kind of data in the training.
Yes.
Maybe the test data are more fair or like more optimized for one LLM.
Yes, so in this research, we use the zero-shot learning. So we did not train this model. So we used the proprietary available GPT-4V model and the Lava latest version that was available through Olama APIs. So we did not train them. So yes, there might be some disadvantage for Lava for showing this poor results because of the training set of data. But also I wanted to highlight the fact that if GPT-4V and Lava, the most generic versions, show this much results, then if we learn our own model, then the performances would be even more higher.
Thank you for your question. Any more questions? Okay, let's thank the speaker one more time. Thank you. Last but not least, we have our second keynote. This
Do I turn my audio on
Yeah,
here?
turn audio on, turn video on, share a screen. Then this is not showing. Try. It was on and off this morning. You can see. Something. Oh. Yeah, it's not showing. Use mine. What do you think? Yeah, just share your screen now. Use mine. Okay. You can still put it right here. You have it here. So I'm gonna make it a full screen. Yeah, there you go. So yeah, you can still press it. You're not on mute, right?
I don't think so.
Okay.
Yeah.
Go ahead.
Yep.
Okay. All right. I hope folks on Zoom can also hear me. And I'm acutely aware that I'm standing between you and lunch. So yeah, so let's move forward. All right, so I'm going to be talking about scaling autonomy. And so of course, autonomous driving is what I like to call a keystone problem. So it's really a problem of our times, and pretty much we need to solve all of computer science to get it to work, right? So it's a rich ecosystem of hardware and software. And we know that mobility and autonomous driving is now transforming to an AI problem. There are diverse needs globally. If you're interested in propagating these things uniformly across the world. And there's a critical social value that we derive from this. It's a human, mobility is a human need, but also autonomy has long-term consequences for human development. And the opportunity of autonomy, I like to relate it to what happened with communication. Essentially, we had 100+ years that went between telephones to the advent of smartphones. But really what smartphones meant was that not just communication, but we also had freedom for recreation, occupation, and all sorts of stuff that we do on our smartphones. And I think autonomy is a similar transformation where we are going not just from mobility to everything that we can do in cars and how they relate to everything that we do in the digital world. Right. And going back to when Henry Ford founded his company, he really saw the car as freedom of mobility. Right. And if you're interested in these sort of things, then of course it's a $1 trillion market. Right? Now, it's not that it's a solved problem in many senses. Now, we do see self-driving cars on the streets around us nowadays. And really, just like any other field, there's a lot of AI that we have in the mobility problem too. But the expectation, once we have AI-based mobility solutions, is that it should work in all sorts of scenarios. And by definition, something like autonomous driving is a long tail problem, right? So there are all these sorts of known and usual things that we train for. But then what we really want to deal with is the unexpected long tail of the distribution. And that is critical for such safety conscious applications. And really the way in which this is approached nowadays is lots and lots of human and capital investment, where we go through these cycles of detecting issues, curating data, training our models, verifying them, and repeat the process. And the main focus that I'd like to bring to this talk is essentially to realize that there are lots and lots of advances that have been happening where we can automate the entire pipeline of training, simulation, and verification through advances in language models, diffusion models, vision and language models, neural rendering, and so on. So what I'd like to propose is a rebuilding of autonomy stacks with a focus on scalability. And we can think of the traditional things that we do with driving as part of one foundational model where we can do open world perception and planning. But then we cannot possibly see everything in the world and plan for everything in the world. We need to have simulation mechanisms, and really we cannot know in advance what to simulate. So there need to be ways in which we can automatically transform our videos to simulation test beds. But then doing simulations by themselves is not enough. We do need to go ahead and figure out ways in which we can automate the training, verification, and data curation parts of what the simulations are giving us. And these things lead to complex workflows that the autonomy development cycle entails. And progress with LLM agents is one way in which we can automate these complex workflows. All right, so, and the stuff that I'm going to talk about, these are things that we also try in real world cars. So a lot of these things do work in real time and do have the behaviors that we want for these safety critical applications. Okay, so let's start by talking about a little bit about the DevOps part of autonomy. Now, as we know, autonomy DevOps is really a continuous process that involves both field and the data center, right? So we have cars which are driving around, which do the data collection for us. But then in the data center, we need to be doing the model training for everything that is needed to drive. But these trained models are going to encounter issues. We need to have ways to find what these issues are. We need to figure out how we are feeding more data to be able to resolve these issues, update our models automatically, verify again, and so on. So, and this is what, as we have discussed just now, is really expensive to scale, right? So we have all these sorts of known issues, cars, known things like cars, pedestrians, and so on that we encounter in the world. But then there's a long tail of everything else which is out there that we somehow need to deal with. And the traditional development cycle of finding issues, curating, training models, and verification, and repeating the process is something which is very expensive. What we propose is to use large language models and large vision language models as a way to significantly automate this pipeline, and hopefully that leads to reduction in capital and operating expenses. So, so the first step in this is essentially an issue finder, and we can think of this as, let us say we have a deployed object detector. We also have powerful, large foundational models that can give descriptions of images, and we can essentially determine using these VLMs what things are present in the image which are not detected by an object detector. Now, having this, we need to do something about it. We need to curate large-scale data to be able to resolve this issue. So suppose there's a construction vehicle that we have not been able to detect with our existing detector. We would query a large vision language model to create essentially a text embedding out of this and query a large-scale image data set to retrieve potential images where we might see similar descriptions. Now, having retrieved these images, remember, we want to solve a localization problem. For example, if we are doing perception, and pretty much everything in autonomous driving, we want localized outputs, right? So in the case of perception, we would then use an open vocabulary object detector to determine in these retrieved images where there might potentially be the object of interest, in this case, a construction vehicle. And these are now our pseudo labels, which are going to be noisy, and they go into a self-training mechanism that accounts for the higher noise in these pseudo labels. And having this self-trained model out, we then need to verify it. And for that, we can have an LLM to generate scenarios, again, retrieve images that match these diversity of scenarios. In some of these cases, our model is going to satisfy these scenarios, and in some cases, it's not going to. And for those places where it does not satisfy these scenarios, we go through a continual learning pipeline that essentially will eventually resolve these scenarios. Right? And once that happens, we are through the verification step for this particular issue that can then get deployed. And this process can keep repeating as we keep finding newer and newer issues. Okay, and so the key thing that I'd like to emphasize here is that this is a process that is fully automatic. And the most expensive part of this data curation process is to do all the road testing and the extensive resources that it requires. So it turns out that in our experiments, there's something that can significantly reduce the cost. So to achieve 2x better accuracy for a deployed object detector, we can reduce 40x the cost, and most of it is essentially the annotation cost. All right, so now a framework like that, of course, relies on foundational models that can give us descriptions of images, that can detect objects for us, and so on. Right? So, so one aspect of this is to do perception, and to do perception in an open world with an open vocabulary. And this is something which has, of course, advantages. It can enable better safety decisions. For example, if we can distinguish an old person crossing the street versus a young person, it can enable better control decisions. If we find a car with an open door, the chances are that we want to go give it a little bit more of a leeway as we drive around it, and more reliable decisions, because these foundational models are likely trained on very, very large scale data sets. And in comparison to standard object detectors, and really what is deployed in all the cars around us today are standard object detectors, which have been scaled with a lot of information for nuanced semantic categories. We resort to large-scale text and reference expressions data sets. And the hope is that we can get robust, highly accurate open world models that can scale to all sorts of new scenarios that we can prompt them for out of the box. So, and this is something which clearly has advantages. So if we detect something as a taxi instead of a car, it means we can expect a person stepping out of it. If we see a person in a wheelchair, then we need to have a different driving decision around them. If we detect kids instead of people, then again, we can have different driving decisions around them. So, so the label space for such an open vocabulary detector is essentially infinite, but it is also something that can then give us all of these abilities. So, so the detector that we have is trained on millions upon millions of images, and it's a transformer backbone, but we have also figured out how we can get this to run efficiently on a real car. So this is something that does give us outputs at a high enough frame rate that we expect for such autonomous driving applications. And of course, the secret sauce for all of this is data, but also one of the other techniques, like how well can we ground these detectors in real images, right? So because we resort to a lot of language data for training these, but as we know, language data can be ungrounded. So we have for object detection, negative control is a significant problem, and we figure out better ways in which we can ground these object detectors through generation of negatives. So compared to things like YOLO World or OWL V2, which are well-known open source and open world object detectors, we have significantly higher accuracies. Now, besides open world perception, open vocabulary, open world planning is also important. And state-of-the-art planners are essentially rule-based, and they work really, really well, right? So, so of course, there's a lot of push for end-to-end planning, but the fact is rule-based planners handle 99.9% of the cases really, really well. But they do break down in some scenarios. For example, there's a state-of-the-art planner from the winner of the New Plan benchmark last year. And in this case, it cannot handle a particular complex scene and collides. So the white car is the eco car. It collides with oncoming traffic from a cross street. Now, using language models, we can do better reasoning that can help resolve these types of scenarios. But also, a critical aspect of this is just language models by themselves are not sufficient for solving a planning task well enough and to be grounded well enough. So our approach to this is essentially rule-based planners are known to work very well. Language-based models can reason well. So can we combine the external knowledge of an LLM with the grounding of a rule-based planner? And what the LLM is doing here is not giving us trajectories. The LLM is giving us the parameters of a rule-based planner, the ones highlighted in yellow out there, the parameters of the rule-based planner that we should be tweaking so that we are able to navigate this complex scenario well enough. And there's an approach that works pretty well. So on the New Plan benchmark, for example, the blue bars that you see are, so New Plan is a pretty saturated benchmark, by the way, although it is pretty recent. But the blue bar is ours, and the gray bar is a state-of-the-art rule-based planner, and the orange bar is basically an ungrounded LLM. right? So essentially LLMs are great, but we do need to ground them and combine them well with what is known to work well for the planning problem. Another critical aspect of what is needed for the scalable DevOps pipeline is to have foundational vision and language models. And now some of the aspects that we do care about here is these, just because of the scale of autonomy data that we typically work with, data center costs are really important. But at the same time, lower hallucination is a critical need. So, so we develop particular ways in which we are able to meet these dual goals of efficiency and lower hallucination. And critically, for a problem like driving, LLMs are not very good at certain types of reasoning, for example, spatial reasoning. But this is also a sort of regime where we do have lots and lots of well-grounded data for solving these type of tasks. So the VLMs that we develop, they are pretty good at spatial reasoning. For example, here, to determine is there a car cutting in, it can reason about lanes, it can reason about distances, orientations, and so on to arrive at the answer. Or straight up measurements like distances. So we train this on very large scale depth data, both ground truth and generated depth data. And it can come up with reasonable answers for getting distances, etc. Of course, besides autonomous driving, these VLMs are also useful for other applications. So just analyzing your drive data, determining whether accidents have happened, why accidents have happened, and so on, right? So, so here I'm just showing that we do get low hallucinations in the sense that if there are no accidents, then the model faithfully says that there are no accidents, but if there are, then it does detect and describe those accidents. Okay, so so these are some of the building blocks that go into this automated DevOps pipeline. But a critical part of the whole framework is that we should be able to do simulations, because we don't really expect that we observe everything in the real world. And as we all know, a traditional simulation pipeline is something which is very, very expensive for autonomous driving, because it involves graphics artists to create assets, graphics experts to do the renderings, AI experts to do the training and the verification. In contrast to that, our approach is essentially to go straight from the data to simulations that are automated and a DevOps pipeline that can take up these automated simulations and feedback. So, and you would realize that to be able to solve something like this, we do need these open vocabulary perception models and VLMs, et cetera, that are coming up with descriptions of the scene that get fed into a simulator to do simulations and thereby to the DevOps pipeline. So one aspect of simulation is for us to be able to create a faithful replica of the world. And for everything that we have observed, advances in neural rendering are great for us to do this. So essentially, given a video that you see on the input at the left, we can create a 3D digital twin of the world using techniques like NURBS and Gaussian splattings and so on. What you're seeing on the right is a 3D reconstruction of the world. And in this 3D reconstruction of the world, we can move the cameras around, we can insert agents, we can remove agents, we can have other types of dynamics for the agents, all with faithful material and illumination properties. So, so I'll skip the details here, but essentially, that particular visualization was a NERF-based approach, and we know that this is in autonomous driving, we are dealing with dynamic scenes. So we have particular ways in which we incorporate a decomposition of the scene into static and dynamic parts, and we have ways in which we can incorporate inputs from LiDAR because we are dealing with sparse views here. So the overall quality of the log replay, as you can see on the right, is very high. So on the left is the input video. On the right is, so no learning involved here, right? So it's a NERF, it's an optimization-based process. We can do things like agent removal. The white car has been removed from the scene. We can do things like agent replacement. The gray car on the right is replaced by a white car. We can do things like agent insertion. So one more car inserted in front of the white car on the left lane. We can do things like sensor variation. And this is important because you can imagine that we have all our data coming from cars, but if we want to put something on a truck, then the height of the sensor becomes different, and we would need to simulate everything for that. Things like changing the lanes. So instead of driving on the right lane as we are doing in the real log, we are driving on the left lane in the simulation. So the real benefit of this approach is that essentially we can go all the way from just having videos as input to a full simulation testbed, where we can automatically do things like replay sensor variations, agent insertions and removals, closed loop simulations, and so on. Right? So now everything that is driving data for us is now a simulation testbed where we can validate our algorithms. Now, things like nerves and diffusion things like nerves and Gaussian splats, etc., give us a faithful reconstruction of the world, but they will not be able to create new information. And for that, we use language-based or language conditioned diffusion models, where we can do things like if we want to insert an arbitrary object in the scene, we just need a text prompt for that. And using text to 3D diffusion models, we can essentially create these arbitrary objects. And this is critical because if we have regular cars and buses and trucks, there's lots and lots of data around for those. But what often breaks down perception and planning methods are these unusual or oddities that we see on the road, right? So, and because these text to 3D diffusion models are pre-trained on lots and lots of real image data where lots of variations have been seen, we are able to create these odd types of objects. And having created them, we can then insert them photorealistically into our nerve-based simulation testbed to be able to visualize, in this case, a sky blue ice cream truck, or if it's a white truck with graffiti, or if it's a green pickup truck with a white trailer, or something like a yellow digging construction vehicle, which is driving down the wrong way. So all of these are things for which we possibly cannot get data in the real world. So we need to, what I'd like us to realize is that it needs a combination of these neural rendering methods to faithfully reconstruct the world, text conditioned diffusion models to get arbitrary 3D objects. But also one missing piece here is how do we simulate the behaviors of the ego car and the other agents once we have inserted a new object in the scene. And for that, we train, again, a text conditioned trajectory simulation model. And this is a diffusion model which has controllability. For example, here I'm showing controllability with respect to time to collision. So the red agent that you see is the ego car. The orange agent that you see is an adversarial car. And what we are doing is essentially controlling the time to simulation as a parameter to a diffusion model. The diffusion model is simulating all vehicles in the scene except our ego car. The ego car is running the planner that we want to deploy, right? So by controlling TTC, we can then create different types of collisions. And because this is a controllable model, then we can have all of these variations. For example, we can create collisions from behind. In this case, you can see a few different such examples. We can do things like create collisions while merging. And again, the red car is running the ego planner. The yellow car is an adversarial agent, which we cause to collide. And the blue cars are essentially everything else in the world. And the blue car and the orange car, they are all controlled by a diffusion model, and the red car is the planner. So again, different types of collisions that we can create using this. Okay, so this is really the first controllable diffusion model out there, which can generate safety critical adversarial simulations. And in comparison to other state-of-the-art trajectory simulators. For example, we can get much higher collision percentages, right? So we want to create collisions for these type of simulators. So we can create a higher percentage of collisions. Now it's kind of easy to create collisions if we perform behaviors which are non-realistic. So there's a need to have high realism and high on-road behaviors. So everyone is kind of doing the right thing, but still collisions happen. Right? Okay, and finally, I'd like to talk a little bit about how we can orchestrate complex workflows using LLM agents. And so the key here is that everything in the autonomy workflow is something where there's a lot of human expertise that's required. We would have a new simulation task, a new testing task, a new training task, which we would convey to a developer, and they would use the known tools which they have at their arsenal and then write code for solving that task. And we want to automate this process to essentially have LLMs as code planners. And now, of course, we want these code planners to be very well grounded in the tasks that we want to solve. So everything that we solve with perception models, VLMs, etc., and really all sorts of non-language based tools that are also available are potential tools that the LLM can deploy. Right? Now, besides that, we have knowledge bases. We also have what I'd like to call LLM deficient functions. So things like arithmetic, things like logic, constraint satisfaction, and so on. These are all tools that are available to the planner to orchestrate in a program synthesis way. And a critical bit here is the reinforced self-training, for which I'd like to talk a little bit. So now LLM agents, of course, as zero-shot agents are very, very well known. They're very well used, where we would have a query that goes into a frozen LLM, and then a program which comes up with a program that gets executed. But what we really want in many of these scenarios is the ability for the planner to be responsive to the things that it is looking at in its environment or encountering in its environment, which means that we need to train the LLM to be able to work well in this particular environment. And so in this case, then it essentially means that the program that the LLM is generating needs to be somehow fed back to the LLM with a particular reward. And we can use reinforcement learning for this. Right? So now a challenge for the type of, and this is, so reinforced self-training is a well-known paradigm, of course, in training LLM agents. But a challenge for tasks like autonomous driving is that these are kind of complex workflows. And it is very hard to have training data which covers the whole trajectory of how the workflow is actually solved. So the only thing that we have available in most cases is going to be the final answer, which would be a binary reward of whether we succeeded in solving that workflow or not. So what we have been developing are ways in which we can take these sparse binary rewards instead of dense neural rewards for entire trajectories and develop self-trained LLMs that can do such code deployment tasks well enough. And so this is something where with much smaller model sizes, we are able to improve upon larger frozen LLMs or similar sized LLMs, which are not self-trained. And once you have this, then you can think of asking the LLM agent to answer questions, which kind of reduce the burden on a VLM to solve these same problems, right? So if we want to ask, can you turn right here? We could just push this into a multimodal LLM, but a better way to solve it potentially is to have the code planner generate code, and this code will orchestrate things like object detectors and other LLMs if needed to be able to come up with the answer. For example, for can you turn right here, an intermediate result that the code comes up with is that it should detect all the traffic signs and then determine if turning right is a possibility. Or can I go straight after the stop sign? And in this case, the answer is no. because you do have these signs out there saying that you cannot enter a one-way street out there. So there's also something that can solve other applications besides autonomy. For example, in insurance applications, there's a need once an accident has happened to determine responsibility ratios, as in two insurance companies would negotiate to say that your guy caused 30% of the accident and my guy caused 70% of it, right? So to be able to solve these type of tasks, we need to have an extensive set of tools and knowledge bases at our disposal. And the LLM agent is then able to orchestrate these tools and knowledge bases to be able to come up with the answers that we desire here. Okay, so I'll stop here and just to quickly recap. Scalability in autonomy is a critical challenge. Although we see self-driving cars everywhere around us, the fact is that they are very, very expensive to deploy and scale. And by leveraging advances that we are making with large language models and ancillary areas like diffusion models and neural rendering, we hope that we can automate a significant part of the autonomy development cycle. Okay, I'll be happy to take any questions.
Exciting talk, and yeah, we can take some questions.
Thanks for your excellent presentation. And just the how reinforcement can improve the performance of LLM that you introduce to use reinforcement learning to improve the mechanism, the workflow. And I want to more details about this.
Yeah, so typically in a REST-like framework, we would train a neural reward model, and this neural reward model would be trained on entire trajectories for a workflow, right? So if your workflow is that I want to do perception, then I want to do simulation, then I want to send it to a trainer, a verifier, and so on, then now this whole thing is a complex workflow, and you would possibly, the chances are that you have very little data for which we call trajectories for this entire workflow, right? So, but what you can have is whether the verification succeeded at the end or not, right? So, and so what we are developing are sparse reward models that work with this binary signal of whether the verification succeeded or not, to be able to train better for these type of workflows. Now, having said that, I think such sparse reward models, I think, are great because I believe they are more adaptable. So you can use similar types of development methods because you just need the final yes or no answer, right? So if I have a different workflow that I want to train for, the same things work. But the fact is they are inefficient in training compared to if we did have a dense reward model. So what we are also looking at are ways in which we can generate trajectories more efficiently by interaction with the environment, right? So building good simulators for the entire workflow rather than simulators just for driving scenes is one piece of the puzzle there.
Any more questions from the audience?
It's more a comment. I struggle a bit with your section where you talk about openness, right? So you talk about open world, open actions, and so on, right? I have the feeling. I mean, it's nice how you address it, and I never thought about it. It was really nice to see that you say, okay, you use also this diffusion model to generate a caterpillar, right? But the caterpillar is still a concept which is somehow the data, right? So for me, and I come from the classical AI perspective, so it means I don't have a concept, I don't have a grounding for something, right? So what would happen if you, I don't know, you drive in, I thought about the last 4 minutes about good example, but something like that, you drive on a rural area in Africa, right? You might see things you have never seen or you never imagined, right? And you don't have a concept, right? Would this come up here somehow magically? Because I still have the feeling it has to have somewhere in your trained model already, right?
Yeah. Yeah, so I mean, I don't think there's any getting around the fact that these things require to have seen everything, right? So, and if you're talking particularly about diffusion models for simulation, Things like Stable Diffusion have been trained on like 5 billion images and so on to begin with. So chances are that they have seen everything in the world. But at the same time, there are also definitely going to be cases where diffusion models break down, right? And we see that all the time. So for example, so maybe not so much for 2D diffusion models, but 3D diffusion models happen to be more brittle compared to 2D models because 2D models trained on 5 billion images. 3D models have been trained on order of millions of images, right? So we are orders of magnitude away. I don't think that just data is going to take us there. I think we need good physical methods that bridge this gap, which allow us to essentially figure out where things are breaking down and have physically based mechanisms to fill in the gaps there. How I like to think about these is I don't think methods like this mean that everything is 100% automated or mean that we just have things running 24/7 and they are kind of learning by themselves. Rather, how I see these is that instead of having AI experts in the loop or graphics experts in the loop, what we can do is have domain experts in the loop. And that, I think, is the real empowering thing here, because the cost of autonomy is essentially that you have machine learning and computer vision and graphics people who are designing autonomy pipelines, and they are not necessarily transportation researchers or people who are automotive researchers who are doing that. So what these automated tools can provide us, hopefully, is that people who are on the field and people who are encountering these things like rural images of a car driving down a rural road in Africa, they are able to take these images and they are able to then enhance these models by themselves without having AI experts in the loop.
You don't have any more questions? Thank the speaker. Thank you very much. Good talk, and that wraps up our workshop this morning. So we're gonna post the recording on the website. Again, go to our workshop website. You can just search Thank you everyone online. So the workshop ends. Thank you everyone for attending.